Everybody has had a good night's sleep. How many of you went to the sauna yesterday? Let's see some hands. 2, 3. 3 of you went to the sauna yesterday, which is a good sign. It's better than 0 people going in there, so we are on the winning side, I would say, at this point. Welcome to the Thursday, I'd say at this point. My name is Lukas Raatikainen, and I will be once again speaking some of these intermediary discussions here throughout the day. We're going to first start with space situational awareness track, and first off we're going to have Ari-Matti Harri discussing that topic more in depth. Let's welcome him to the stage with a round of applause. Welcome. Here is the remote. The stage is yours.
Oh, thank you. Thank you very much indeed. So good morning, everybody. So I'm Ari-Matti Harri. I am from Finnish Meteorological Institute, and I'm telling to you about National Space Situation Awareness Center. That was the founding decision was done in December 2024. So and around 1 year and 2 months ago, and we are currently ramping up this activity. And motivation for that kind of National Space Situation Awareness Center comes from the fact that there are many things in near-Earth space that seriously affect human life and human technical systems. And they also, the impacts of space phenomena, they actually pose dangers also to society and harm. They may harm normal societal life. So firstly, when you look at this picture, when you look at the lower left, you can see the Earth 57, 90, and then 2000. Actually, the last picture is about around 2025 nowadays already. So that gives an impression how much and how many objects are flying around the Earth. So the near-Earth space was almost empty, or virtually empty, until 1990. And the amount of objects orbiting the Earth has increased dramatically during the last 3 decades. And currently, there are more than 40,000 objects that are being catalogued and followed and surveyed around the Earth, objects that are 10 centimeters or bigger in dimension. And then there are objects that are small, that are 1 millimeter or more, and the amount of such objects increases 100 million. There may be 200 million, well, we don't know exactly, but there are immense number of them. And all of them, they actually pose a threat to those space-based infrastructure, in expensive satellites and important satellites that are serving the society. Because when impacting, even a small piece impacts a satellite, it may cause severe disruption. At least, if the satellite is not dead, at least the service will be disrupted. And that is why those are being surveyed and tracked all the time nowadays. It was started by US, and Europe has now its own system to do that too. And FMI and Finland is part of this European system. Then there's space weather on the right-hand side. Space weather is caused by the sun. It causes disruptions for satellites, for satellite-based services, and even ground-based infrastructures. That is, those impacts we know, and we have been following them and serving them for a while, or giving service out of them. But that's also important near-space impact for us. And thirdly, NEOs, near-Earth objects that now and then, asteroids and comets, Now and then they pass close to the Earth, and they also may pose a threat. All of those are part of space situational awareness. We want to know what there are, what there is, and whether they pose a threat to us or not. So, the founding decision to have a National Space Situation Awareness Center was done in December 2024, and it will comprise of the main center or headquarters. It's at FMI, and then that operates in close cooperation with the National Land Service of Finland. So we jointly run this center. And as I told, so there are the three major components. SST, space surveillance and tracking. We keep knowledge of those objects around the Earth. We follow space weather, and then we follow NEOs. We can say that the global space situation awareness picture we will get through cooperation with in European system that we are part of, and then US SSA systems. Those are the ones with whom we create a big picture, and then with our own service, own observations and analysis, we refine the big SSA picture for national needs and national requirements. I want to say in the beginning also that this European Space Surveillance and Tracking System, EUSST, is also already running in the background, and our National Space Situation Awareness Center actually covers it, so that EUSST is inside FMI's or Finland's EUSST activity resides inside our National Space Situation Awareness Center. This European Space Surveillance and Tracking System, it does have a global network, so network of radars, optical telescopes, and laser telescopes. And one of the laser telescopes, or candidate for that network currently, is the laser telescope in Metsähovi by National Land Survey, and it's being, just now as we speak, it's being upgraded with a power laser. And that's the telescope in Metsähovi. And it's currently being used for geodetic purposes, so it will observe satellites that are having geodetic functions. And in 1 year from now, it will have the capability, it will have a power laser, giving it the capability to detect also dark objects that actually don't have reflecting surfaces and might not be willing to be detected, and then also objects of debris and such. So this is the way that this nice telescope will be part of the European Space European Space Surveillance and Tracking Organization, EUSST. And as I mentioned, that's one integral part of our of the National Space Situation Awareness Center. This is a general picture of the center itself, and so the headquarters in the middle, that resides at FMI, and then we are running that together with our partner NLS, National Land Survey, and it has these three components: space surveillance and tracking of the near-Earth objects, space weather, and then tracking the debris and satellites around the Earth. These three objects. And this is something that we may think that might be quite expensive. Well, it's not cheap to run, but it's not that expensive because we already have a 24/7 Center for Space Weather Service. It's a global space weather service for ICAO, and it has 24/7 service and ISO 9000 quality system. So this National Space Situation Awareness Center will be built as an extension of this existing space weather service, and that is why it's a fairly non-expensive system to ramp up, and that's why we also got funding for this. These funding decisions was made in December 2024, after actually a struggle of a couple of years, including all the ministries of Finland. Now, there will be also, so we can say that we will have two kind of centers, so the civilian purposes and then another one will be for military purposes. This lecture and presentation focuses on this civilian system only. We will have, there's our database in the center. We will have front ends around that, above that, and then an analysis and application layer in between. We have built the database, and we do have got preliminary front ends done. We are working on the application layer, and as I mentioned, it will be operational in 1 year, in 2027. Let's put it that way. I think in the next one, we have to do this one first. So this is the ramp-up schedule that we have. So that, as I mentioned, by 2027 should be ready. That's what we have. We have an agreement with our ministries and funding organizations that by November 2027 it's fully operational. Very likely it will be a little bit earlier than that. However, that's our final goal. Currently, we are working on this, on the user, the service system to help our operators and forecasters that are in the operational line, giving services and responding to questions and requests for information. So that will, this system very likely is ready in 1 year, and then operational system will be much later, by the end of 2027. This is just a glimpse of the forecaster viewing system that we currently have, and it's being updated, and actually more functions will be added to the system all the time. But already we are able to see the objects, their orbits visually, and of course in print, and then for space weather, status of the sun, that's the main thing. All of those data we can visualize and display for our forecasters. One note is also that this NOE, so it's part of planetary defense, and we can talk about that after this talk, if there's any time. Then use cases, they can be seen here. I've noted I've done my work, so conclusions. So this National Space Situation Awareness Center is ready and operational in 2027, and it is a 24/7 service, ISO 9000 quality system. Thank you.
Thank you for this. Ari-Matti. Do we have any questions from the crowd regarding this topic for Ari-Matti? And obviously you can go bug him later on with way harder and in-depth questions on this topic. If no questions as of now...
I have one question myself. So that when I talk, why did I mention planetary defense? Well, that's an integral part of this. NEOs, they pose a threat for the Earth system. That's why we need to be aware of that. And then for the data, we rely on cooperation with US partners and then European partners. But we also do that, follow them ourselves. And we also have a partner in Helsinki University who are experts on NEOs.
Good question and good answer.
Thank you.
Thank you once again. One more round of applause for this presentation. Asking from the technical side, do we have the next presentation online? Apparently our next presenter is not online and not here, so we're going to actually jump to the next presenting party straight away, if that's okay for you, Eija. Eija has agreed to go right away. So next up we're going to move to space hazard effects in polar regions and how Eija has managed to tackle that in his latest article. We're going to hear more next on this topic. With a huge round of applause.
So good morning, everybody. So this talk is about space hazards and their effects. So very relevant to the previous talk and activities described in that talk. So I will describe today few results about ongoing projects, C-SPARC and Safe Earth research program. So polar areas are special. They are very much hit by the space disturbances. The effects are coming in those areas where we typically see auroras, or close to those areas, not exactly, but close to those areas. And that's why there have been centuries-long tradition to measure, to have instrumentation in those regions, to measure what is happening in space. And the space is also easily accessible from those locations, and all the effects are stronger than in other areas. So this is one example on ongoing projects, C-SPARC. That's an International Space Innovation Center nominated as a COSPAR Center of Excellence. And what we are doing there together with international partners is that we study how the space is affecting to the technology as well as humans in space to enable safer space exploration in future. Our team, STO team, responsibility is to study sun and how does it change and how does it affect to us in polar regions and how we can predict future disturbances. So few results about C-SPARC. So contrary to the conventional wisdom and common knowledge, the largest space hazard effects are not seen during the sunspot maxima. And I will show you that more in detail. Norway, the northern lights are the most common. So northern lights are a visual signature about space hazards, but they are not happening exactly at that place where the most strongest effects are seen. An example is also following on that. And here it comes. So I'm showing to you 4 different phases of the sun. 2 of them are quiet, and during maximum time, there are a lot of sunspots, what we can see with the instrumentation. And few years after that, there are very complex and big ones, which are strong. So geomagnetic activity follow a similar cycle. You can see the typical sunspot number there with a green curve. But the solar activity doesn't follow that curve, but it follows. The largest activity is seen when the strongest and most complex sunspots are in the solar surface. On the right-hand side, you will see the latitudinal distribution where the energy is targeted, where it is hitting. I will show it more in detail in the later slides. But to summarize that result, sunspot number doesn't describe how active sun is. It describes a certain form of activity, but that shouldn't be used for predicting the effects. But something else should be used, and we are working on that, and we have a good hypothesis of what should be used. Another research, there was a defense on this last year. That research showed that the energy coming from the sun is distributed much more regionally than expected earlier. So earlier it was expected that all the energy distributes evenly to the huge space, but that doesn't seem to be the case. But instead the energy goes through the very thin channels, and they are hitting certain places, and the regional differences are very large. And that needs to be taken into account when planning exploration missions and when estimating how to protect the ground-based infrastructure. This is one European-wide project funded by European Defence Fund, which is targeting space environment and space conditions. It's also, in addition, building European autonomy what comes to the satellite safety and how they can protect themselves. A national initiative very much related on those 2 previous international projects is our Safe Earth research program within University of Oulu, which is part of Profilization 8 program. And that is a program combining 3 elements: space safety and security, cybersecurity, and human safety and security. And with those 3 elements, we build better situational awareness and improve the resilience in Arctic regions and in other regions as well. Then 3 example results from the previous projects. So this is about the latitudinal distribution of the energy, what comes from the space. And when we studied with 10 different magnetometer stations how the energy is distributing over the latitudes, we realized that it's not actually distributing evenly, but it goes to the certain places. And that certain place is 70 degrees geographical latitude, which is, corresponds to the 67 geomagnetic. So that's where over 40% of the energy is hitting. And below Arctic Circle, it's only 10% of the energy dissipating there. So that's important when we build resilience for ground-based technological systems. So how the energy dissipates in a different way when we study seasons. That's what you can see here. And during winter time, the role of polar cap is larger, so meaning that most of the energy will go to those places, and all the physics that is driving for that dissipation and all the atmospheric processes, those needs to be considered what are happening in the polar cap. And then in summertime, most of the energy will come to the auroral oval, and then we need to study the processes related to that, which is typically magnetotail processes. So then third one, we typically study, when we study how much energy we are getting from the space and from the sun, we typically study all the frequency ranges together, or some specific frequency range like for pulsations, PC5, PC2, PC3, PC4, and so on. But we also, in this study, we wanted to understand that how much does it matter that which frequency range we are using. Because when we are choosing instrumentation for doing our studies, that's when we define what we are seeing. So it's extremely important to choose the instrumentation wisely. And it's good to know beforehand what you can detect with each of the instrumentation, what are available. And sometimes you need to develop a new one when you realize that none of the existing instrumentation will do the work what you are wishing them to do. So this study gives a bit input for that. And what you see here is different frequency ranges and how much energy is coming through PC5 pulsations, or through that energy range practically. And that's a distribution over the course of the day, so daily distribution. And the color coding gives you the information about the energy, how much energy is coming. And when you see the most bright or strongest red, then that's the area where you get the energy. And from this plot or series of plots, you can clearly see that there is a big difference depending on which frequency range you are studying. So the shape of the structure is pretty similar, but then also from this series of plots, you can see how regional the effects actually are. And it needs to be taken into account in very many different studies and when planning missions. When we are flying through those areas where this strongest energy is going through, then instrumentation, for example, should be turned off. And it's important to know exactly when that happens. Otherwise, the instrumentation will be turned off for too long time, because the observation time should be always maximized, but also without taking the risk of breaking down the very expensive instrumentation. So that's the reasoning behind this study. So to summarize, with CSPARC, Center of Excellence and Safe Earth Research Program, we have found out that the largest effects of space hazards are seen during declining solar cycle phase, which is typically 2 to 3 years after the solar maximum. And the physical reasoning is that that's the time when we get the most complex magnetic structures, and those are the ones that are capable of carrying most of the energy. And also, although aurora's northern lights are important visual signature of particles coming from the space, it's not exactly giving the information where the largest effects are seen. But roughly, sometimes, depending on the phenomena, sometimes the largest effects are in the southernmost border of auroral oval, but in some certain cases, they are in the northernmost border. And we should understand how the Sun-Earth coupling works during different phenomena. And the latitudinal distribution is important for understanding which infrastructures and important assets to protect. So not to build overprotection, but not to build underprotection. So with this summary, I will end the talk, and thank you for listening.
Thank you for presenting as well. Let's open the discussion and questions related to this topic. Do we have any questions in the crowd as of now? One question in the front. Let's hear it right away.
Hi, thank you. Great talk. My name is Ryan Lambert. I'm with the SETI Institute. So one thing that I found interesting is you mentioned that sunspot maxima doesn't actually correlate with when you are most likely to have the largest space hazard effects. And instead, it's the complexity of the spots. So do you have a way of quantifying spot complexity, or is there another tracker involved? Okay, so you do.
Yeah, sure. I didn't present that, but yes, there is a way of showing how complex the sunspots are. That has been done now over 2.5 solar cycles, the identification of the magnetic complexity of the sunspots, and we have studied it, and we have papers, so I can send it to you. And other one is in a press, like almost out there, so I can send that information to you. And it's actually, there are several different methods, but it's mainly visual, because we are looking sun from the distance, so we need to do it visually. But there are a lot of theories also what we can use to better understand why sometimes we get that complex bipolar sunspots and sometimes unipolar. So yes, there's a lot of information about that. And we have produced a different sunspot number based on that. So it's available.
Excellent. Thank you so much.
Further questions regarding this topic? So basically, if I want to see like really good aurora borealis, I need to wait for the complex sunspots. When are we going to get those? Out of academic curiosity, I'm asking.
Always after solar maximum few years, but you can always see auroras in some places. There is always enough energy in the magnetotail and magnetosphere to have aurora. So we don't need to wait for big events, but if you want to see very complex ones, then it's better to wait.
Good to know.
Yes.
Any other questions at this point? If nothing else, one more round of applause. Thank you for presenting.
Thank you.
Thank you. Next up, we're going to have a presenter coming online to us. I don't even know from which country, but do we have the presentation online ready? We could be good to go about now for the next one. And with a huge round of applause, let's go online.
Start now. Well, good morning to everyone. It's an honor for me to be here with you, and I apologize for not being able to be there in person. I am David Galeano, and my team is composed by Juni Peltoniemi, Rogerio Enriquez, and Jose Guichard. I'm going to present our project entitled Trajectory and Speed Reconstruction of Sub-10 millimeter Space Debris Through Satellite Swarms with Active Illumination. The presentation is going to be divided in 5 points, as you can see in this slide, with a brief introduction to then pass to the description of the coincident in-orbit laser sheet particle monitor on the labels COLA, and the extension of COLA into a satellite swarms that we called COLA SWOS. Then we are going to compare the performance of both detection concepts, and from the results and discussion, we are going to develop our conclusions. So as has been mentioned in previous presentations, the use of the space debris is a growing problem that has alarmed some space agencies. In the case of their monitoring, there has been multiple advances in their detection with ground-based observation techniques. However, for debris larger than 10 centimeters, there is some limitations on the ground-based space observation methodologies, and for their study, we rely on probabilistic models that are developed with collisions that have been monitored over the Earth's orbit. Here we have an example of these probabilistic models for particles smaller than 10 centimeters. This is a result from MASTER, that is a software developed by the European Space Agency to predict the particle flux. on a given orbit. On this example, we simulated an orbit of 800 kilometers for the year of 2023. So on the left, we can check out the flux particle and label it by diameter, and on the right by kilometer. In the plot of the right, we can see also the classification that master gives to the debris, given their origin. So we can check that there is some paint flakes and some meteorites that includes the background of the meteorites population. As I mentioned, there is some difficulties to detect debris smaller than 10 centimeters with ground-based methods. So satellite-based missions have been encouraged during the last years. Two examples of these satellite-based concepts are the light sheet anomaly resolution and debris observation called LARADO, that is developed by NASA, and the coincident laser sheet particle monitor that I mentioned, COLA, developed by ESA. Giving a brief example of LARADO, on the left we have the detection concept through a laser sheet and a camera. Has been already tested in a vacuum chamber in a laboratory setup. And on the right, we can see how they reached the detection of a particle of 1.5 millimeters with a CCD camera. Going now to COLA, it's still on the simulation stage. So it takes the debris population from master, that is the Space Debris Terrestrial Environment Reference that I mentioned it in previous slides, and computes the satellite position using the spacecraft planet instruments in matrix events, also called SPICE. With this, this software or this code is designed by NASA and is used to predict the performance of interplanetary missions with a good precision. Finally, to predict the instruments and response with the particles that we are going to study, at FGI, there were developed some light scattering models of samples that resemble space debris. To extend these examples of COLA, we have on the left the detection concept using two laser sheets that are going to be observed with a CCD camera as an image sensor and with an avalanche photon diode sensor as time tagging sensor. So we have these two instruments that are going to allow us to compute the particle's trajectory. On the right, we have an example of the samples that resemble the space debris. In this case, on the photo, we have an angle rod that is of metal mainly. So now that we have presented the detection concept, I will show you in a brief idea of how are we going to compute the trajectory of the particle. So we start positioning the spacecraft from SPICE, we get the reference frame given the x-axis with the spacecraft's velocity and the z-axis with the Earth direction. So now on this reference frame, we compute or better say we define the instrument's orientation. So with a given azimuth and a given elevation, we can compute the new reference frame where the instruments are oriented with the variables that we defined for the observation. In a better description, here is like the visualization of the reference frame. As I mentioned it, the z-axis is going to be on the direction of the Earth. And if we know the entry point of the particle that is going to be taken from the master simulation, we can then compute the exit point with the velocity direction of the particle. So on the right, we have the entry point as x sub I, and the particle velocity as v sub p. So with this information, the distance between the lasers and the normal of each laser, we can compute the exit point of the particle if we have a detection in the first laser sheet. Then with the distance between the sheets, we can compute easily the detection, the difference of the time in both detections. So now Passing to COLA SWOS, we are going to add 5 satellites to the COLA detection concept. They are going to be aligned with the COLA satellite, and they are going to be in the same flight of direction. But on this case, we are going to change the laser sheet configuration to a laser beam configuration. So now we are going to have the particle illuminated during all its trajectory through the satellite swarm. So now the beam of light is going to be the first satellite, that is the COLA satellite that I mentioned before. And with this, we are going to compute the response of the instruments in all the satellites that compose the swarm. Here is an example of the detection. On the left is the geometrical configuration of the swarm, where we can see that they have a maximum distance of 50 meters between the satellites and a minimum distance of 35 meters. On the right, we have the orientation of the instruments. So you can compare, or you can see how each number labeled satellite is oriented given the satellite swarm's geometry. And for all the cases, the detection instrument or the detection sensor that are going to be the APD sensor and the CCD camera are going to have a field of view of 70 degrees. So now that we have our instrument configuration, we define the classification of detections. So we are going to rely on the signal to noise ratio at the image sensor and the type tagging sensor, and we are going to compare it with a given threshold T. So we use the models, the light scattering models developed in FGI, and then compute the background to determine the signal to noise ratio. Given this, if we get only one detection in the COLA and COLA source, we are going to consider the particle as detected. In the case of COLA, as we have 2 laser sheets, we need both detections to give a reconstruction of the particle's trajectory and speed. In the case of COLA source, we are going to compute 30 detections during the trajectory of the particle crossing the field of view of the swarm. And if we reach more than 2 detections on the Colas-Ross concept, we are going to consider that the particle trajectory and speed can also be reconstructed. To execute the simulation, we gave Cola the field of view of 70 degrees in this as the same of Cola's was, and the laser sheet power is going to be 15 watts. Here for Cola's was, we are going to use the same power, but to boil the laser beam, we are going to divide all the field of view into 9 lasers. So each laser is going to have a divergence of 7.7 degrees, and in this way, we can cover all the field of view of 70 degrees. Passing now to the results. Here is the result for COLA. On the left, we have the sheets that I mentioned before with some trajectories for the particles that we computed. We did the simulation with 1,000 particles, and we retrieved the classification from master, as can be seen in the image as on the right. So here we can notice that the most detected particles are the white paint flakes, and also more than 90% of particles detected. However, the reconstructed trajectories and speed are lower than the 50%. On the other hand, here on the left, we have a representation of the trajectory of a white paint flake over the satellite swarm. So in the blue circle is the main satellite, that is as the COLA satellite, and the triangle is going to be the particle crossing all the field of view. If we compare the detected particles with COLA, we notice that we get lower particles, but this is a consequence of the distance that the particle has to cover in the satellite swarm in comparison to the distance between the laser sheets. In this case, in the previous case, the laser sheets are at a distance of 2 meters. Meanwhile, in the Colas concept, each observer can be over to 50 meters from the laser beam. So the distances here are an important factor. So retrieving the results from the plots that were presented in the previous slides, we noticed that COLA is like a really good concept method to reach detections. However, less than 40% of the trajectories can be reconstructed. And in the case of the speeds, we reach like less than 5.6% of the reconstructible particles. However, in Colaswos, we were able to make more reconstructed particles, reaching more than 40% of reconstructed trajectories and reconstructed speeds, with a reduction of the detected particles. That is a consequence of the distance of the swarm, as I mentioned it before. So these results demonstrated the utility of both concepts to detect space debris smaller than 10 millimeters. In the case of Colaswos, we reached and we improved the number of reconstructible particles in front of Cola with the detection concept of 2 laser sheets. On the other hand, we will seek to implement Cola's detection concept with laser ranging. This LIDAR concept reaches better detection rates, and we will seek to improve this type of sensors, as the LIDAR doesn't use a CCD camera and computes the photon count directly on a photon counter. So we are going to, as future work, complement our Colaswos concept and compute the reconstructible trajectories and speed, and try to compute also the shape and material of the particles. Thank you very much for your attention, and here are some references used during the presentation.
Let's get one round of applause for this presentation.
Thank you very much.
From what I understood, you are also checking our YouTube live, so you might actually have a chance to hear the questions. If we have anything in the crowd, I can bring you the mic and we can get the questions all around to him at lightning speed. Do we have any questions in the crowd regarding this topic? We have one question. Can we get the mic over there? Can you confirm that you are hearing at least my voice right now? Or you can ask your question and then we can just tell him in Zoom as well.
Sure. So thank you for the talk. It was wonderful. My name is Ryan Lambert. I'm with the SETI Institute over in America. You maybe have mentioned this and I just missed it. How far out are you able to detect these smaller than 10 centimeter particles?
I'm looking at the technical guys if they got it. He's already gone, so you can email the question later on to him, and hopefully he'll answer. But yeah, let's get one more round of applause for that presentation. Email him later on with the question, so you actually get the answer. But regarding the topic, now that you had your question, now it's time for you to present as well. Do you want to speak on this mic? Okay, excellent. Welcome to the stage, Ryan, from SETI. Nice. Search for extraterrestrial intelligence. One of the huge keen interests I have, but I'm not going to bug you more on that later on.
We can talk about it afterwards.
Okay, sounds like a good plan. With a round of applause, let's get Ryan to get his presentation going.
Sorry, I've been trying to make sure that I don't go over time, so I set a timer in my pocket so I'll know when to hit 13 minutes hits. Thank you very much for having me, everyone. My name is Ryan Lambert. I work for the SETI Institute over in America, the Search for Extraterrestrial Intelligence. Obviously, this has nothing to do with aliens. But today I'm going to be talking about SkyMapper. It is a decentralized observing network for satellite detection, something that is meant to give satellite operators more flexible tools than they might have otherwise with the current SSA infrastructure that governments provide. But before I get started on that, let me talk a little bit about the problem as I see it that SkyMapper is trying to solve. I don't think it's a particularly controversial point to say that space is busier than it's ever been. We've seen a huge explosion in the amount of satellites that are being launched into orbit. More and more are going up every year. And that means that space is getting more congested, and it's more important than ever that we know exactly what the environment is like, that operators are able to make decisions on when they need to do a collision avoidance maneuver, and are aware of not only what the environment around them is like, but what their satellite is doing as well. The IAU, the International Astronomical Union, has actually, astronomers, I'm an astronomer, I didn't mention that. Astronomers have a love-hate relationship with satellites. They tend to get in the way when we're looking at something that's really faint and far away. So International Astronomical Union keeps track of how many satellites are in the sky and how many satellites are planned. And right now there are over 500,000 planned satellites for constellations that planned for by 2035. Now, most of those aren't going to see the light of day. A lot of those are going to stay on paper, but it gives an indication of exactly how congested space is going to get in the future. And so the problem is that I'm speaking from an American's perspective here, the U.S. Space Command. I feel very nervous having talking after the Finnish SSA architecture talk. But the U.S. Space Command is really a wide breadth. It is cataloging satellites and it's updating them, but it's really only updating them once a day. So if you want some more specific information about where your payload is, if you have a maneuver planned and you have just made a maneuver, you're going to have to wait an entire day before you have an update on what the orbit of your satellite looks like. Same thing for your competitors or anybody else around you in the space environment. If they make a maneuver, you might not be aware of it until the next day, and then all of a sudden you have to make a collision avoidance maneuver. It's also especially frustrating during times, especially like post-launch deployment, where orbit computation can take days. So you have this point where your satellite is in orbit, you're wanting to run tests, you're wanting to get it to the final altitude where you can begin your mission, but you have to sit and you have to wait to figure out exactly where your satellite is. And then US Space Command, at least, I'm not sure what the EU SST provides, has no special monitoring during critical mission phases. You really are stuck with what you have. If you need moment-to-moment feedback on what your satellite is doing, you're not going to find that based on the current architecture that's available. So the idea of SkyMapper is to provide operators with that moment-to-moment feedback if they want it. With more frequent monitoring, especially during times like post-launch deployment, you can cut down the time it takes to get an orbit computation during post-launch deployment from days down to hours. You can more quickly detect when you need to make a maneuver, or you can more quickly get an update on what the orbit looks like after you've made a maneuver for your satellites. This gives you more lead time on alerts for collision avoidance maneuvers that need to be made, and that lets you make better decisions, gives you more context, and you have more time to weigh your options. And the last thing is high cadence observations or photometry. This is something that I never really had thought about until joining this project. Photometry can reveal whether your spacecraft is tumbling. I actually have had a satellite operator reach out to me before. They said this satellite's not really responding the way that we expected and we need some eyes on it. Can you go and look at it? So I did. I spent a couple of weeks trying to find exactly where the satellite had gone. Sure enough, when it was in the field of view of my telescope, it was blinking like a lighthouse. And that was what let them know to narrow it down that one of their propulsion mechanisms had malfunctioned and it had spun up. They no longer had a satellite, they had a top. So that's the kind of information that can really help troubleshoot when you aren't getting a response like you expect from your satellite to understand what's gone wrong. But that's not available for you when you're using the traditional SSA architecture available to you through like US Space Command or possibly EU SST. And that's the gap that SkyMapper really wants to try and fill. So I mentioned SkyMapper is an American startup. It is building a global network of optical telescopes that's able to cover the entire night sky. This is kind of an interesting network because it's not all one type of telescope. It's a mix, off-the-shelf smart telescopes that anyone could buy, you and I could buy and use in our backyard. It's a mix of that. It's a mix of professional astronomical observatory style telescopes. The common denominator between all of these is the sky bridge, that's what connects them to the network. So you can see in my little diagram here, this little blue box that's next to each telescope, that is the sky bridge. It is essentially the brain of the network. It talks to every other sky bridge in the world, and it talks to the telescope capable of remotely piloting that telescope and taking observations, downloading the data from the telescope, and uploading it to the final server. This network is essentially controllable from a command center called Sky Viewer, and that's what's in the center here. It's a website right now that you can log into, assuming you have credentials given. You can log into it, you can take control of a single telescope if you want to, remotely pilot it, look at whatever you want, or you can put in an observation request and watch as the network takes the observation for you and the data rolls in. So you're able to see that data as it comes in, and that all happens within minutes of you putting in an observation request. So in order to act as a network that's useful for operators, you have to have a lot of stations. So it's important to ask, where is the network currently on that front and where is it planning to go? Right now, SkyMapper is in beta. It's been in beta for about a year doing tech validation. So there are around 60 telescopes that are connected. Most of them are in the US, some of them are in the EU. We even have 2 of them here in Finland, which is pretty cool. But the plan is to rapidly expand the network to 1,000 telescopes by the end of 2026. 1,000 telescopes was picked because that is the estimated number that we need to be able to see any target on sky within 7 minutes. And that accounts for weather, that accounts for single telescope malfunctions, that accounts for some user forgetting to turn their telescope on so we can no longer connect to it. But the idea is that once we have 1,000 telescopes, we should be able to see any target that you want within 7 minutes, assuming it's on the night side of the sky. If you're trying to see a satellite on the day side of the sky, you're out of luck. These stations, once we've got them deployed, we're going to be prioritizing high and low latitude coverage because there are a lot of missions that prioritize high inclination orbits, sun synchronous orbits, polar orbits. These are all of interest, especially for Earth observation missions, but they are incredibly hard to actually image because they spend very little time on the night side of the sky without being in the Earth's shadow. So ensuring that we have stations both in high latitude and low latitude regions means that we can cover even those satellites that otherwise are very hard to see. And the way that we're planning on exploding the number of telescopes from 50 to 1,000 by the end of the year is exploiting the fact that we have very low-cost units, very compact units. Like I said, the SkyBridge is really all you need if you have a smart telescope. We have users that own their own smart telescope are interested in joining the network. All we have to do is send them a SkyBridge. They connect it to their telescope, and boom, we have a station. But not only that, we want stations where maybe there aren't people, because we don't always want stations that are just located around cities or even in the countryside. So by the end of the year, we're planning on building autonomous domes, essentially little domes that we can place out into the middle of nowhere, stick a telescope in them along with a SkyBridge, and as long as we have power source and internet connection, which we could do through like Starlink or something, then we have a remote station that is autonomous and capable of handling itself. So let's say you want to take an observation. What do you actually do? Right now, we have that web portal, like I said. You have a website that you actually can manually go through and control the network if you want. That's great, but it's not necessarily efficient for operators. The plan is by April 2026, when SkyMapper goes live, is to have a form that users can fill out, either programmatically, so an API that you can fill out multiple times a day or multiple times a minute if you want, or a form you can fill out manually. It's very simple. You just identify the target. You identify the observation cadence. So do you want multiple observations per orbit? Do you want multiple observations per day? And specific times that you would like to observe if there are any. Once you've submitted the form, the request goes into the observing queue. The SkyMapper network is going to be constantly going through this queue and divvying out observation requests to compatible telescopes. So when your request makes it to the front of the queue, a free telescope that has the correct field of view and is confirmed to have a clear night sky will be assigned that observation, and the SkyBridge that is connected to that telescope will essentially slew the telescope to where it needs to go and tell it to observe at the time it needs to observe. Once the observation is complete, the data is on the telescope, and the SkyBridge downloads the data from the telescope and begins to encrypt the file and split it up into smaller pieces and store it on the blockchain. From there, the encrypted file fragments end up going to a Web3 blockchain-based server. It's essentially a cloud server called a Kaleva, and from that server, the user is able to retrieve their data. This is something that will happen all within minutes of having the observation. I don't want to belabor the point on Web3 because it's not really my forte, but from my understanding, it's an incredibly secure system. So it ensures that operators know that the data that they are receiving has not been tampered with, it's secure, it's been validated, it is exactly what the telescope saw. So you can be sure that no one has tampered with your data and that what you're seeing is reality. And then some essential services. So SkyMapper, it's great that it can get observations for operators. It can monitor your satellite in the night sky and give you some images of it, but there are other abilities as well. So getting astrometry of your satellite as it moves through the night sky over multiple observations capable of determining orbits. So updating you on orbits specifically after maneuvers, or if you would like to confirm that your satellite is where you think it is. Conjunction analyses, threat assessments, so making sure that we give you alerts if it looks like there is going to be a collision. And like I said, giving you some extra lead time on that alert that you may not have if you're using traditional systems. But my opinion, the most important tool is the critical operations monitoring. So if you have a point in your operation where you need moment-to-moment feedback, this is the service for you. The ability to observe during post-launch deployment, the ability to observe during reentry, some rendezvous missions, things like that. If you have any time that you would say, I need to move this telescope, or I need to know what this telescope is doing at this exact moment, it can really help in your decision making. SkyMapper is capable of doing that for you. It's able to get a telescope onto your satellite anytime in the night sky. And that is it. I have a little timer in my pocket. It hasn't gone off yet, so this is the quickest I've gone through. I know I don't have any interesting graphs or fun figures, so I'll end here with some observations that we've taken using the SkyMapper network. So on the left is Shenzhen 21 and Shenzhen 25. After a potential refueling rendezvous, this is two Chinese satellites, possibly the first rendezvous in geostationary orbit ever, our first refueling in geostationary orbit ever. So we saw them shortly after they undocked. EGS is a LEO satellite, and for whatever reason, it has a glint every time we observe it. So we've observed it 6 or 7 times now. You can see, this apparently didn't save, it's supposed to be looping these, but you can see it flashes very brightly for a moment as it goes through. That has to be a quirk of the geometry and the orientation that the satellite is in right now. So the astronomer in me would really love to know what it is that's causing that reflection and get them to stop it, because that would ruin our images. But it's very, very cool to see otherwise. And then the last observation is a rocket body, the Chinese rocket body Long March 8A that they left in orbit back in September. It's very bright, which is annoying for astronomers, but it also makes for a very cool video. So that's it for me. Thank you very much for your time.
Thank you, Ryan. I think we have time for a couple of questions at this point, and it's nice to see somebody who's doing more words per minute than I am here in the stage, so thank you for that. Questions from the crowd at this point. Let's go first over there, at the back.
Oh, thanks. It was a great talk. I have 2 questions. Firstly, apparently your system is based on like citizen activity, and you mentioned there's a startup around 2, and then so you need to have some kind of revenue logic, I guess, in your back pocket. So what would it be? And then secondly, this is really interesting, and I'd like to, let's say, talk more to you during coffee break concerning like EU's SST system and you. But then in the US, have you had talks already with the US space track, and then there's this TRAX system is emerging within NOAA. So do you have those talks underway just now? So these 2 questions.
Yeah, so the first question about the revenue, the idea is that operators will pay for the observations. So if you have some persistent monitoring that you want, there will be a fee associated with that. And I believe the plan is also maybe not to compete with the satellite catalog, but to also build our own database, SkyMapper database of objects in the night sky, and give access to that for people who want it. So that is where the revenue is primarily intended to come from, is from users who are interested in using these services. They'll pay for them there. In terms of talks with the US infrastructure, so TRAX is a great one. I actually don't know specifically, so I would assume that my boss, Frank Marchis, he is the CEO. I know that he is in talks. I think he is in talks with them, but I don't know for sure. I can't confirm. But yes, we're aware of tracks and we're aware of the SatCat and the existing infrastructure that is built around it, and we absolutely want to work with them because this is, the way I see it, SkyMapper is really more designed as a tool for depth, whereas the tracks and SatCat are built for breadth. They cover everything in the night sky. Maybe they don't update it as quickly as you want or as often as you want. And if you need more nuanced information there, more fine control, that is what SkyMapper is there for. So I do believe we're planning on working with them.
Good. Good question. Any further questions at this point? Front row.
Thank you for a very interesting talk. And thanks for showing those very impressive capabilities and future plans. Are there any limitations for those autonomous domes, what you are planning to install in terms of Arctic conditions, for example?
So I do not know the specifics on the domes. I wish I did. I know that they exist. I don't think I have the slide here saved where I could go through and talk about them. I am not sure what the plan is on deciding stations. I know we had thought about, yes, putting some in the Arctic, specifically up in northern Canada, has been floated. I think the main issue is ensuring that we're putting it on land with people who agree to let us do that. And so that's the main thing, is we want to make sure that we're working with people to put these stations down, and we're not just throwing them down on someone's land and without them knowing. But yes, that's when you were talking about the Arctic and having to worry about the radiation and having to decide on that also clicked in my mind. That's something that we have to think about.
Thank you.
Mm-hmm.
Good. Any other questions? No questions at this point, but I have a suggestion for you. Yeah. Next year, book a stand to this event and bring one of those domes here, and then we can all discuss, like, should we put one in our backyard or something like that.
I'll do that, and I'll talk slower next time while I am at the booth. So that's...
Okay. But hey, thank you for presenting. One more round of applause for Ryan on this thing.
Thank you very much.
Okay. Next up, we're going to actually have a coffee break for some time, and there is one general announcement here at the exhibition area at the Danes, Denmark space, space, something like that. The Danes, anyway, they have a tasting menu there apparently, so they told me it's not going to be rotten fish, so it's going to be something actually good, so please visit their stand to actually taste some Danish treats. Not rotten fish from what I've heard. But yeah, we're going to be back here in about half an hour. Enjoy the coffee, enjoy the tasting and everything. See you then.
Check, check. Check, check. Check, check. Check, check. Check, check. Sound test. Sound test. Check, check. Riittääkö? Check, check.
it on? Yep.
this much away. Testi. Hopefully you can hear my voice even to the back. My name is still Lukas Raatikainen and I will be chairing this session as well. We're going to keep on with the space situational awareness as of now. And I just told Eric that like when people hear my voice outside of this room, then they start walking in. So welcome. There's still plenty of spaces in the front row as well. No need to be standing at the back unless you actually want to stand at the back. But there's plenty of seats for everybody. We're going to be here for the next 45 minutes with the same topic as in the previous session. And first off, I'd like to welcome to the stage Eric Siem to discuss more in depth about this topic, and let's get him to take a huge round of applause. Welcome.
So can everyone hear me? That's great. So today I will speak a bit about from mission to supply chain, the industrialization of access to space, as we currently see that we are in a transformation from a research and development driven industry to a real industrialization. So in the first stage, I will speak a bit about my background, then a little bit about my company where I started the research from, then I redefining the supply chain in the space, then supply chain in the space age. Then I speak a bit about systematic challenges in space logistics, then we will have a short strategic outlook. So, short about me, I'm the CEO and founder of ZL Space. I'm an expert in space logistics and supply chain operations, and I have a quite extensive background in time-critical and mission-driven logistics, and right now defining the so-called SOG logistics, spacecraft on ground, as we have in the aviation AOG, aircraft on ground logistics. So I have a quite deep industry insight across launch, payload, and orbital operations, and I try to build end-to-end logistics solution for the space sector. So our company is focusing on logistics services for the space industry, quite good in time-critical handling of mission-essential cargo, and we have a deep understanding in space industry requirement and constraints, especially when it goes the next step to industrialization. We secure compliant handling of sensitive high-value assets because we have direct airline access, we are IATA member, and so on, and we can offer a door-to-orbit service from a logistics perspective, and we are built to have a zero-failure environment and tight launch windows. So I now redefine the supply chain in the space age. In the first stage, we have the terrestrial supply chains. Then we will see orbital supply chains in the next years. We will see lunar supply chains. And if we go further, we will see interplanetary supply chains and interstellar supply chains. So terrestrial supply chains. These are all supply chain operations we will see right now going on Earth. These are the classical supply chains we see in industry and across all types of logistics. They are representing the baseline on how supply chains function right now, and they will be the base for every higher supply chain. If we want to build up orbital supply chains, we need, first of all, working terrestrial supply chains onto the orbit, and then we can speak about orbital supply chains. And right now, we have a lot of research going on terrestrial supply chains. So then orbital supply chains are, per definition, all supply chain operations are within the orbit of a planet and its moons. These are currently in a very early stage of development, and they will represent the next evolutionary step of supply chain in space. If we want to have continuous operations beyond Earth, like permanent lunar operations or even missions to Mars, we need to have a solid supply chain in the orbit. Otherwise, all stuff will fail. Then it is highly relevant for in-orbit manufacturing and assembly, because I hear the first startups thinking about orbital mining, orbital manufacturing, mining in the asteroid belt. If we don't have a solid supply chain and logistics in the orbit, it will be for sure fail, as we can make a great manufacturing there, but if we can't bring it to Earth or from the satellite belt to the factories, we will have no chance. And it's a very critical enabler if we speak going to Mars, because I hear a lot of projects about Mars colonization, permanent presence there, and if we don't have solid supply chains to the orbit, in the orbit, we will not see this. Then we speak about lunar supply chains. They are all supply chains, operations between celestial bodies and its moons, and between the moons of a planetary system. They can originate on the surface or in orbit in both directions, and they connect planetary and orbital supply chain layers. And they enable sustained activity beyond low Earth orbit. And they are a key requirement for permanent lunar operations. If we don't have working supply chains to the moon, we will not be able to have a permanent base, what the US plans right now. So, as I mentioned before, I have the topic interplanetary and interstellar supply chain. I will not go deeper in it because this is very experimental at the current stage. So, the architecture of space supply chain. Each layer operates on a different level, but all are part of one integrated system. You can't have a lunar supply chain without a terrestrial supply chain. Then they are built, each supply chain should be built to interact with each other, and a single supply chain can start on orbit and can be extended to deep space. If we extend the whole models, we can go even to other galaxies or other universes technically. So space logistics is not fragmented at its current domain. It goes across a lot of domains. And it's the first basic conceptual model. It's not like a fixed model. It can be extended. It can be modified in the future. And it provides a framework of thinking how the future access to space have to be and will be. So the supply chain in the space age, I first will speak a bit about the historical foundations, then about the current space supply chains, and then I will speak about the industrial future of space. So the historical foundations where we had a very mission-based approach. We see Apollo, it was like one mission taking 10 years to get it launched. The costs are very high. Everything was primarily government financed, and it was research and development driven. And there was no real focus on scalability and budgets, which of course we see we had very high budgets in the space industry. Now it's going to change. As we see in the current space supply chains, we see the transition from mission-based supply chains to industrial-based operations. We still have a very strong research and development feature inside. We still see companies are developing, but the first companies are starting to industrialize themselves, and they must now think about how to make a sustainable supply chain. Otherwise, they will have problems with future orders, with future scalability. And we see an increasing launch frequency, in some cases nearly daily. Like, I think the US were last year at around about 220 launches, and a rapid emerging new startups. And a lot of the startups are very early stage. They think about research and development, not yet about supply chain and logistics. And right now, our growing bottleneck is access point to the orbit. We need more launches. I think sometimes we can have 100 launches a day and we still don't have enough launches available. So the industrial future of space, we will see orbital factories, we will see in-space manufacturing, we will see resource extraction in the asteroid belts, we will see dedicated supply chains going there, we will see a continued growth in launch frequency. I'm quite sure we will see routine human access to orbit and potentially the moon in the coming years. We have a lot of thinkings about it. Also, if you look around, we see an expansion of space tourism, and for this to make it sustainable, we need a development of supply chains to make it possible, because to sustain a satellite in orbit, you don't have the human factor, but as soon as you have human in space, you need certain resources to be ready to go there. So the systematic challenges in space logistics. So one of the biggest bottlenecks is customs and regulatory authorities. We have a quite experimental environment and an ongoing development from research and development to industrialization. So first of all, customs and regulatory authorities. We have in comparison very small shipments with a very high value, like 5 million, 10 million is nothing, and the boxes have like 30 times 30 times 30 centimeters. They are mostly classified as dual use, which means you need to explain a lot to the customs officers. Excuse me. We have very limited operational experiences inside the customs officers. And we have sometimes very long, unpredictable approvals of getting cargoes like this released. And this causing a high risk of delays in the entire supply chain. So we see also a very highly experimental environment. Because we have very limited experience outside of the space industry in handling cargo, many partners in the logistics field underestimate the technical and operational risks coming with it, and space hardware is often handled as regular cargo. I heard stories where seals were broken, where they just approved customs inspections for clean room logistics, where satellites were sent out by DHL, which is for me like how this can happen. And especially the lack of knowledge in bigger companies who claim to be logistics companies in the space age, and authorities cause a lot of frequent errors in the whole thing. And this is a high likelihood in errors and timing and documentation. So you can very easily have a huge shipment destroyed just by making errors. So to see the ongoing transition from research and development to industrialization, many space technology right now in the stage, they are focusing on research and development. They are very limited, aware of end-to-end supply chain requirements. Their processes are designed for prototypes, for launches. They are not designed for industrialization scale-up. And they have a very high risk of costly errors in the future development. When they really need to scale up, if they get orders like they need to launch in the next 3 months like 10 satellites, and they don't thought how to bring them right now to the launch sites, if they don't secure the launch sites on time, the launch capabilities, it's nearly sure that they will have errors and problems in the future. So a strategic outlook. We will see for sure continued growth in launch frequency in the next years. We will see a rapid industrialization of orbital operations, which is going on right now. We see supply chains to Moon, Mars, and the asteroid belt, especially when it goes for asteroid mining. And I think we will see a new space race, which we see like it goes more national. We see a lot of fundings going in this industry. So ideas for the future. I'm sure we will see more orbital transportation services. A new upcoming topic over the next years will be the return logistics, when satellites will be returned to Earth, when we have missions from from other planets or from the asteroid belt. It needs to be returned, and then we need to ask ourselves how we can make it safe from orbit and then on Earth to the final factory. I'm sure we will see logistics hubs in orbit and on the Moon, because without a logistics hub over the next years, we will not be able to have a sustainable supply chain. And an idea for our company is maybe we will have the first office on the Moon. So thank you for your attention, and are there any questions?
Thank you for the presentation, and as said, do we have any questions in the crowd regarding this topic? Let's start with the front row right away.
Thank you for your presentation. I found it very interesting. Horizontal exploration. Are you looking at recycling? Because you're talking about logistics, return, and so on.
About return logistics, first of all, from an industrial standpoint, which means when we have orbital manufacturing, if we have all exploration, the satellite belt, we will specifically see that the resources need to be brought back to Earth. This resource is then distributed, which means we will see landing sites where we will bring the relevant cargo to, and from there it needs to be distributed. Also, a big topic in the next years, this is maybe something we will see after this. Right now we have a lot of experiments going on, like if you heard companies who planning launches, bringing experiments to orbit and bringing it back. And this experiment then need to go back to their research facilities. And for this we have a lot of open questions we don't really deeply think about yet.
Good question, good answer. Any other questions from the crowd? One there at the back, if you can get the microphone there.
Sorry to be all the way in the back. My name is Remco Timmermans. I'm wondering if I look at this foresight, this future that you're painting us, any of us going to be alive when that happens? What is the time frame that we're talking about?
How we see what's going on right now, I think we will see the first exploration, the satellite belt within the next 10 to 30 years, but it's very experimental. I really don't know it. It really depends on the funding. If we have, like, if the government support stops from one day to another, I'm sure it will take longer, but I'm sure there's a good chance we will have it in our lifetime, especially for the students right now.
But does it make sense to start thinking about that now, start planning about it now when we're looking 30, 40 years into the future?
It's very essential to think right now, because right now we build up the orbital logistics, and if we don't build up the orbital logistics right now, we will not be able to make supply chains ready for them. And we should build our supply chains and our logistics in the orbit right now ready for interplanetary supply chains, and also for supply chains to the asteroid belt. Otherwise, we have a supply chain amazingly developed for operations in the orbit, maybe to the moon, but nothing behind it. This will be an essential challenge we will face then. So we should right now think already beyond, so we are ready when it gets actively going on.
Good questions. One last question here in the front, and then we move forward, because I want to ask one question myself as well.
Thank you, really interesting
here. Have you made any studies in European or maybe Nordic supply chains when it comes to orbital capacities and capabilities?
When it comes to orbital capabilities, I have not studied so much here in the Nordics, but what I see the biggest issue we face right now going to orbit is that spaceport are located in very rural areas, and it's not the infrastructure there. Like if you go to Andoria right now, we have two options going there. They are Widerøe and SAS, and both have not really cargo capabilities getting the satellites there. So this is the issue we face, getting the orbital supply chain done.
You mean down further south?
For the launch, because orbital logistics right now is in a very early stage. We have the first fundamental ideas about it, but this is something we need to develop right now to be ready when it really becomes active.
Okay, I think that I could contribute to other solutions for going south.
Being
representative of Space Sweden North, and also sitting here together with my Andrea exchange.
I'm always happy for this to have an
Yes, thank you so much.
Yes.
Good. One final question for myself. What do you think are the three first companies / organizations that will face these logistics problems?
I don't want to name names for compliance purposes, but I can say we have one company who is an exhibitor here where I'm sure they will face this issue in the next months. We have a company in Germany who was about to launch yesterday. I'm sure they will face also these issues, and there are plenty more companies. Okay. I think I said enough. I don't want to speak too much for compliance.
Okay. Thank you for the answer, and thank you for the presentation as well. Thank you. Next up, there was a question about recycling, these kind of things, but we're going to continue on that kind of topic with circular economy, space industry, with Kai Lindholm, with round of applause. Let's welcome Kai to the stage.
Thank you very much. Good morning, everybody. let's talk about circular economy and circularity, especially for space. I think the presentation is not ready yet. My name is Kai. I work with Fraunhofer. Fraunhofer is a very large research association in Germany. I'm located in Berlin, and my background is actually circular economy research. So it's not that much focused on space, but the presentation hopefully will show you what is linked between circular economy on Earth and what solutions exist there and what can we transfer actually into space. Looks like we need another 20 seconds. Everything's fine. All right, now it's working. So let's go on, circular economy in space. You might have possibly heard about circular economy on Earth. So actually I'm quite happy to see that pop-up poster over there. And if we talk about responsible consumption and production patterns, it's goal number 12. This is what we are actually talking about. And on Earth, we have a transformation from linear economy that basically consists of the elements take, make, and waste, transforming to recycling economy. But actually the future should be more or less circular economy. That means that we keep resources in circles, but not only resources like in the recycling economy, but also parts, for example, sub-assemblies, assemblies, and entire systems. From a circular point of view, that means we have three major focuses. The first focus is on narrowing the loop. That means we have to reduce the consumption of resources. That's the red circle over here. That means, for example, we have to rethink how systems are designed, how systems are actually manufactured, and how systems are actually ready to use. Before they are ready to use, they are going to be produced or manufactured. In this case, we can slow the loop. That means we have everything to do to extend the lifetime of a product. And extending the lifetime means we have to repair products. For example, we can reuse products, we can also refurbish products, and we can remanufacture products. And last but not least, if every other R strategy, so-called R strategy, doesn't work, doesn't count anymore, then we can look into the field of end of use for recycling and repurposing. So what does it actually mean? Down here is the life cycle of a product. An ordinary product could be a washing machine, car. What you see there in the blue line is the estimated environmental impact. Most products we use actually have a high environmental impact during production and during use, and basically also end of life. On the other hand, the possibilities for influencing circularity is the other way around. We have a high impact when we rethink, for example, product systems, when we refuse, for example, and when we reduce the resources we should use. And the impact decreases with the other R strategies at the end when it comes to repairment, refurbishment, for example, remanufacturing. And last but not least, the last R strategy is recovering, but this is mostly energy recovery. So the basic idea is now, how can we transform those ideas of a circular economy from Earth into space? And there's the so-called Kármán line, which is a boundary between everything that I told you counts on Earth and what doesn't count actually so far in space. So what we actually want to do and what is actually working on Earth is validated and proven solutions for all these R strategies in various sectors, for example, automotive industry, and take those ideas and transform them also and put them into visions and initial approaches for space. The European Space Agency published some white papers about it, and there you can also see different approaches, how they want to transform those ideas that are valid on Earth into the space. For example, orbital assembling, orbital refueling, orbital manufacturing, refurbishment, and so on. So those are the same approaches where we have proven solutions on Earth. And we would like to transform those ideas also into space. So that means the same circularity approaches that I've shown you should also count in space. But the question here is, what is actually the environmental impact? Because the environmental impact is basically on Earth. And from a space perspective, test and launch, for example, has the highest environmental impact. And the question is, can we lower this environmental impact by using other R strategies that have an indirect impact into, for example, test and launch into manufacturing? So we identified basically 5 different R strategies that can be transformed from Earth to space. First one is orbital manufacturing. It's nothing new, of course, as an idea, but it's basically that we have to rethink entire systems in this case. So we start very early in the design process, in the ideation phase, to rethink how systems are designed and how systems can be used. And the benefits should be, for example, that we reduce the environmental impact during launches by reducing mass, for example, but also to enable the closed-loop resource cycles if we have strategies and technologies in space that can recycle, for example, material. And this is also a closed loop. If you look to the right, recycling in space means that we can decompose assemblies, that we can decompose any system and recycle the material that is included actually in the system. On Earth, it's already working, but we have to transfer those ideas and technologies into space as well. In between, there are 3 other R strategies like repair, refurbishment, and remanufacturing. So let's have a closer look into repair. That means we have, for example, regular inspection and servicing to detect the current status, monitor the status actually of any system. And we should also think, how can we add repairment functionalities? And on Earth, of course, it's working. And from a space perspective, it should be to prevent mission losses, to reduce space debris, and of course to maximize the system value over time. When it comes to refurbishment, it's also quite interesting because that means we renew components and subsystems. So we have to combine this also with the rethinking phase. When we rethink the system, it has to be prepared to also renew components or, for example, sub-assemblies of entire systems. And so we can upgrade parts and upgrade assemblies. For example, to extend operational lifetime and, of course, to reduce material demands. And last but not least, decommissioning in terms of remanufacturing. That means that we can disassemble and reprocess any product, any system, for example, modules, components, and exchange them for the same function or new updated functions in the system at the same time. So that means we can reduce new launches, and of course we reduce the raw material usage. So that's a basic idea behind it. Some approaches are already evaluated and tested, and the circularity vision is actually to develop not only a closed loop circularity on Earth, but also in space, and especially in combination with space. So when we looked into this field, we also made research and scientific study. We identified only 9 scientific papers that take care about circular economy in space, and the basic findings of that was that there are no evaluation, no assessment possibilities so far. So that is also quite a hurdle, because if we want to follow any of the R strategies, we need any kind of assessment, any kind of validation, any kind of testing. So it's not given so far. Furthermore, we need more analysis of the different strategies. It's just strategies, so any strategy has to come into operation, and we have to figure out how can we take the strategy, basic ideas, and operate them actually. And last but not least, we need testing and validation. So that's the basic idea of how we can transform circular economy strategies on Earth into space. And I think we have some time for questions left. Yeah.
We indeed do. Thank you for the presentation. As per said, we do have time for questions. Do we have any questions in the crowd right now regarding this topic? One question in the front row.
Hello to everybody. I'm a component of the recycling. I have some projects regarding the visa. So I'm wondering, do you have any practice or just theoretical model of how has to be solved the problem?
Actually, I didn't really get the question.
Put the microphone closer to it.
Okay, so the question is, have you ever tried anything in practice or just the model of the theory of recycling in space?
If we have ever tested recycling in space?
Yes.
From a financial perspective, not.
Okay, that's my question. Thank you.
But actually, the question is, we are very experienced in technologies how to recycle actually on Earth. And the question always we have is, how can we test and validate those technologies in space? Because you have completely different conditions. And there might be any chance that technology can be transferred. But we don't know it actually, and we are looking for partners to work together in this field. Yes, of course.
Good. Next question over there.
Thank you very much. So my question is, in round-based economical model, many parts are taken care by industry and companies and economy, but the system doesn't work without the public players who have to take part of certain aspects which are economically not viable. How do you see how big part the societies need to take, for example, here, and what is the monetary value of, for example, cleaning the orbits or something like this? How could this work without public, and how much public should actually invest?
Very good question. I took part in last October in a panel discussion about that topic, also together with people from European Space Agency. And I think it's like comparable to circular economy on Earth like 30 years ago. So there was also the initial ideas and existing concepts from the 70s, for example. But the question was, how can we make it also economic feasible? And there was high investments by different governments, especially in Europe, carried out. And still, after 30 years, it's not quite sure if this model really works. So we also have to struggle, and we have the hurdles on Earth for a full circular economy. It works in different fields, for example, where we have well-established cycles, for example, for material recycling. But when it comes, for example, to remanufacturing of parts, automotive industry is quite advanced compared to, for example, electronics industry. So it's always a matter of the different companies that are involved into the value chains. And now the focus shifts a bit from a governmental perspective also into space. And hopefully there will be investments in this field as well. But without any public investment or government investment, it doesn't work.
Good answer and even better answer. Good question and even better answer in my opinion. Thank you for the presentation, Kai. One more round of applause for this. And thanks. Next up, we're going to have Stella. I can take that. Little bit expanding and answering Jan's question actually. Let's welcome Stella to the stage with huge round of applause. Telling more about designing, developing and testing space debris mitigation, remediation and in-space recycling capabilities. Thank you.
Thank you. So, thank you for the invitation. For me, it's an honor actually to present our space debris portfolio, publicly funded. We put 20 million in 2024. So, I'm the program manager for space systems at the European Innovation Council, and today I will tell you a little bit about our space portfolio, the space challenges, and also the focus will be the space debris remediation, mitigation, and in-space recycling of space debris. And some conclusions. So, the European Innovation Council is like DARPA in the US. We fund high-risk, game-changing innovations from very low TRL to high TRL in the European space industry. What is inside the EIC space portfolio? So when I joined the EIC 4 years ago, there were 5 projects. Today we have 55 projects in these 3 domains, with space debris sustainability being the major one, enabling space technologies growing, Earth observation, and meteorology. So many of you think, oh, you overlap, do you work with ESA, do you work... No, we work with DG DEFIS, they define the policies, they're responsible for the relationship with ESA. We focus on high-risk technology innovations. Our interests are in the innovation part. So, these are the challenges I proposed for the last 3 years as the EIC has program managers who define various topics. Actually, in 2023, in space solar energy harvesting, with now 3 working groups on solar cells in space, wireless power transmission, and in-space propulsion. But today we're here to talk about the portfolio of 2024 and why I propose this topic for mitigation, removal, and in-space recycling of orbital assets. I think the previous 2 speakers gave a very good introduction and raised exactly the questions which are extremely important. So, we need green, interoperable, and affordable space debris mitigation and remediation technologies. As you can see, here is some data from ESA, the ESA Environment Report. There are unexpected impacts. Recently, the SpainSat NG, there was also last year, I think it was the fragmentation event. But the big issue is that the collision avoidance procedures are becoming very expensive. Their cost of space operations, collision avoidance, plus technical operation and market risks are increasing. We know that many of the satellites in space are not insured, so debris impact is a huge issue, but not only in the space infrastructure, but also for commercial, for future space stations. Here is just a comparison, data again from the same report. As you can see today, we have space debris greater than 10 centimeters, 54,000, and debris between 1 to 10 centimeters, 1,200,000. So when I was preparing the call, my major question was, how can we select projects which actually can identify and mitigate the debris between 1 to 10 centimeters, because this is a real issue. So this is the challenge we called. I'm not going to deep dive into it because most of you have already read it. But the interesting part is that when I proposed the topic, I also prepared a challenge guide which explained how I foresee the projects to work together. The EIC is unique that we perform proactive portfolio management where projects work together and they create their own synergies. So my main objective was to propose a topic where actually all sizes of debris is addressed, not only small, medium, and large, and all orbits, because very soon, yes, now LEO is overpopulated. Above 700 kilometers, we have space debris clouds, but it is very possible that soon we will have also in other orbits. So these are some of the technologies which came from the 7 projects we selected. I'm not going to dive too deeply. I have to admit that I dreamt, let's let's say, to have many proposals on in-space recycling. Most of the proposals were on how to identify, how to describe debris, but very few on in-space recycling, very, very few. So this is a list of our 7 projects. It was a very competitive, extremely competitive goal, much higher than I expected. So I'm very glad to see some of the projects here, some of the representatives of the projects here. You can see interesting concepts like capture kits for cooperative and uncooperative debris, how to design, fabricate, and test LiDAR transmitter for in-situ small debris. Also look at developing robotic tools and using sensors, space-based sensors. So these are the 7 projects. Now, what's in front of them? Well, they're going to work together in 3 or 4 working groups. And I hope you don't mind I'm presenting this information, but I think it's important. The first working group would work on space debris mitigation and detection. So 4 projects have identified. They themselves said, we want to work on this topic. Second, on remediation. And third one, on in-space recycling. But overall, we're going to have a system engineering working group because their objective is to prepare a strategic portfolio plan in 1 year. So they'll be looking at life cycles, flight qualification. Don't be surprised if in a few years they get the IOD, IOV, and also exploitation of their results. So there are 2 potential areas of synergy which I see. First, within the actual portfolio. So detect, map, avoid debris, but also for remediation, remove it, capture it, detumble it, and look at, identify the debris, but for the recycling, cutting, welding, or manipulation. So when I was making the call for recycling, I was thinking not only for additive manufacturing, but also for mechanical recycling of debris, which is the one most realistic at this stage. Now, what are the other synergies with the rest of the portfolio? As I told you, we have the Pathfinder, we have the transition, but we have also accelerator, and there are some companies who are already also represented. So you can see a lot of our accelerator projects can work also with the Pathfinder ones, and from the space debris pillar, but also from the enabling space technologies. In addition, within the 2 portfolios in the Pathfinder, they could be common project synergies. So you see, proactive portfolio management is a domain which is working quite interesting. What are the activities? We get investors events, we have various conferences, and today is one of these events. Thank you, Jaap, for the invitation. Also, we have portfolio webinars. So last year we had 9 portfolio webinars with having John Mankins, Professor Naoki Shinohara, JAXA. We had 2 webinars from JAXA for the commercial debris removal program. So these are activities, but most of the activities come bottom up from the projects. They collaborate by themselves. So what is the conclusion? By the space portfolio and space debris is unique. Why? In comparison with the other portfolios, because more than 20%, 23%, they're SMEs and startups. This is excellent news, because actually this will permit to the projects to take the innovations and bring them to higher TRL level and commercialization. Very strong interest in ISOs and ISA. And I am very proud to say that the 7 projects we selected in 2024 already know their working group objectives. They're already starting to collaborate. And they will have a lot of opportunities, but for space debris, for in-space recycling, I think it's extremely important. Some useful references. link to the portfolio projects, some other links. We also have a newsletter from the 2023 if you want to learn more about it. And this is the long-term future, which one of the previous speakers spoke, but I do think in-space recycling is an important topic we have to focus in the long term for future cislunar exploration. So thank you very much for your attention.
And thank you for presenting this important topic. We're not going to go into space if somebody doesn't fix this problem in the near future, so you are doing an important work, and thank you for that. Do we have any questions in the crowd regarding this topic? Hands are getting raised the second I say that. Can you start with Jan? He's going to have a tough question anyway, so let's give him the first shot.
I don't have a tough question, but I have a question. Is European programs also helping to test and validate these concepts in space? Space is hard, often you need to demonstrate be in space in order to gather experience to even do something.
Thank you very much for your question. Actually, yes, the EIC has established since 3 years a fast-track IOD-IOV program to the Pillar 2 of the Commission. The European Commission, together with ESA, they have created, but it's mainly European Commission. So for the projects which you saw here, they would have the opportunity actually to get fast-track access to IOD, IOV. It might take a bit of time, but all for O-Accelerator, also for Pathfinder, Accelerate. As soon as you say you're part of the EIC space portfolio, you get that fast track.
Thank you. And next question over there.
So we currently have the issue we can't actively recycle in space. So why we don't go the way for now to make a rule that satellites manufactured by European companies have to either go to outer space or back to Earth by making a controlled re-entry which will burn the satellite?
This is a very good question. Now, this is a very policy-related question, which I would not like to deep dive into it. I think at the moment there is also the zero debris, but there is the technical booklet. But when I was writing the challenge guide, I did make a request for design. So the design for end-of-life services. But it's very complex question which you're asking. And despite me wanting to say what I truly think, I think it's very difficult to answer it because we look only on the technology part. We do not look on the policy. But I know that with the new acts of the European Commission, there is a trend to look exactly for in-orbit satellite servicing or reducing debris and so on. So there is a trend. Europe will be one leading that at the moment.
Okay, but the point is we need a temporary solution, which means until we have solid orbital supply chains for recycling. So is there any plans or any projects going on in the near future to have this ready?
Well, this you should ask the colleagues from ESA. At the moment we have
these two projects, Dexter and Geico, actually working in the in-space recycling working group. So they're actually going to, but this is TRL2, TRL3, okay? So in a few years, you might, or you can even contact them now. But already having in-space recycling as a topic code by the European Commission was quite innovative. So having the logistics part, it will be, I would say you should speak to the colleagues from ESA more actively about it.
Good question, good answer, and one more round of applause, and thank you for presenting this topic. Thank you. Next up, we are going to have the keynotes on this stage, but before that, I'm going to actually ask Jan to come to the stage with me. I want you to describe how has the event gone so far, what have you observed throughout the days, and what are you still expecting from the last stretch before we all go home?
All right, I thank you very much. So we have been going pretty nicely. We have a lot of hiccups on the backstage from time to time from the digital world. We're still developing it. Hopefully it will be better in the future. A lot of people have been networking, so I find this is the strongest part of this event, that people are actually getting know a bit, maybe people from a bit different area than their exact own research field, and they find useful connections to other research fields and other people in Nordics and in Finland. So overall, I think we are, with the whole organizing team, very busy. For example, Polygame from Aalto University students is doing all the streaming and all the digital stuff on the streaming side, and my research group is taking care of the information desk and all the other things. So the whole event is organized without any professionals in this field. So I hope you are you are forgivable for little mistakes what we do every now and then.
Good answer. I don't think you have had applause for you yet, so let's get one round of applause for Jan for making this event possible.
Suffa, tule katsomaan valokuvan täältä mustajälistä. Uffa, tervetuloa valokuvan tänne. Tule tänne ottaa valokuva. Saadaan Janillekin yksi hyvä kuva linkkari tästä näin, kun se on itse lavalla. Se on vaan ottanut kuvia.
Maybe a happy one.
Great job, Jan, you have done so far.
We have a little pause here, and then the keynotes are starting in
10 minutes?
In 10 minutes, yeah. We have given some time. You can fetch quick coffee, and people from other halls will be able to join here, and then we will start in 45.
50.
50, yes. In 15 minutes. closer to the front row. So we still have a couple of minutes. We are starting in a few minutes, so everybody have time to gather here. And the next session, keynote session, is about missions, new missions to far and close, and who is the biggest exploration mission initiator and maker here in Europe. It's of course the European Space Agency. And we see people still coming, so let's wait a couple of more minutes and then we'll start. How has it been so far? Okay, good. All the complaints to me. And if you have anything good to say, then there is an info desk downstairs. All right, I hope everybody start to find their seats, and we are ready to proceed with our next session about big missions in Europe. And as I already said, European Space Agency is our exploration and science agency, and they are making the most incredible missions with the help of the whole scientific community and technology community in Europe. And the next presentation is going to be about the planetary missions of European Space Agency, and I'm extremely glad to welcome on this stage Michael Küppers, who is European Space Agency senior scientist on different kind of missions and projects. So Michael, come to the stage, and let's give a big applause to Michael, and the stage is yours.
Thank you very much. Thank you very much for the invitation, and I try to summarize around 10 missions in 15 minutes. So let's see how that goes. Oops. This doesn't. Yep. Now, thank you. So also just to start with, it may not be the best organization, but those missions are also distributed in several programs in the European Space Agency. So classically, we of course have the science missions, and this is still kind of the core of it. But afterwards, I'll also talk about the mission in the exploration program, the missions to Moon and Mars, and the planetary defense missions, essentially to develop the capability to be able to deflect an asteroid should it be necessary. Starting with the scientific missions. So here are the different science programs starting in the 1980s with the Cosmic Vision, with the Horizons 2000 program, and some of those missions are still in space, so XMM Newton is still running strong, the X-ray mission, and also, so some of the others are in their late operations phase. Then 10 years later, Horizons 2000 Plus program was started, and there I will talk about the Bepi-Colombo mission that is in cruise to its target and will arrive later this year. And kind of the current program is Cosmic Vision, which was developed starting in 2005, and those are most of the missions that are now operating, like JUICE, or currently being developed, like Envision to Venus. And of the small missions, we have in the program the Comet Interceptor mission that's currently under development. And then we have the new program, Voyage 2050. And there we start studying a mission to go to the Saturnian system and land on Enceladus, on Saturn's moon Enceladus. I'll talk a little bit about this. And also we are in the process of selecting the first medium and small mission in that program. This is a little bit a different view on this. It's the missions that are currently in operations, under development, and at the bottom, the legacy missions that have been completed. And again, you can see 4 of the 5 missions in this view that I'm going to talk about. Okay, starting is Bepi Colombo. It's an ESA-JAXA mission for the exploration of Mercury. So looking into all aspects, surface, interior, atmosphere, magnetosphere. To answer the Salat's questions is, why is Jupiter's core so large? So Mercury, of all planetary missions, of all terrestrial planets, has the largest core to mantle size ratio. And one theory is that it was stripped off by a huge impact. There even has been the idea that the proto-Mercury was a planet that collided with Earth in the moon-forming impact, which leads then back to the question where it formed. So those are some of the basic questions that we try to answer with Bepi Colombo. So the mission itself was launched in 2018, has already flown by Mercury 6 times, and will arrive November this year to accompany Mercury, or to orbit Mercury for a year and a half, with a possible or probable extension till end of 2029. So it consists of 2 orbiters, the European planetary orbiter, which will be a close orbit of a few hundred kilometers around Mercury, and the wider orbit of a magnetospheric orbiter that's provided by JAXA. Moving on to JUICE. So JUICE will investigate the Jovian system, will go to Jupiter with a focus on the moons and especially on Ganymede. So the Jovian system, or the Galilean moons, especially Europa and Ganymede, have interior oceans, and we think they may even be habitable. These oceans may even be habitable, and JUICE is investigating them, and in particular has an ice-penetrating radar that will be able probably not to reach the ocean, but investigate the ice above it and draw clues from that. And again, JUICE is quite complete, will observe both Jupiter itself, the moons, and also the magnetosphere that connects all that. Those are the main milestones. It was launched in 23. Had its first 2 flybys of Earth and Venus, will fly by 2 more times at Earth and then arrive at Jupiter in 31. Will have 35 flybys of the different moons, maybe also a flyby for the first time of Amalthea, and then end the mission with an rendezvous with an orbit around Ganymede in late 2034. Next one is Comet Interceptor, which is currently being developed and will be launched in late 28 or early 29. And the star of this mission is a target. It will be the first mission to a long-period comet, and ideally a comet that enters the solar system for the first time, so an object that is as pristine as it gets. And the importance of this is all missions so far have gone to short-period comets, comets that have orbited the Sun many times. And for example, we of course completed 10 years ago the Rosetta mission, which investigated in great detail Comet 67P and landed on it. But it's still, in many of the things we have seen, we still have the debate which of this is really primordial, which is a reflection of the formation conditions, and which of the structures we see formed in the many orbits around the Sun that this object has done. And so a mission like Comet Interceptor, the idea is to go to a fresh object and be able to decide those things. We will have 3 spacecraft, the main spacecraft and 2 probes that will be released a few days before the encounter. One of the probes is provided by JAXA. And another special thing is we don't know the target yet. We essentially wait on LSST, which is going online within the next months to detect our target. And the concept of the mission is it will be launched will be put in an halo orbit around the Sun-Earth Lagrange point L2, and then when it's time, depart from L2 to approach the target immediately when it crosses the ecliptic. Next thing is Envision. It's also in the Cosmic Vision program and under development. And there the idea is to study Venus and the history and the development of Venus. And basically, given that in terms of size and distance from the Sun, Earth and Venus are quite similar, why did they evolve so differently? So the probably most new or innovative part is a synthetic aperture radar for the first time as a different planet that will image the surface in detail and also find out about the development and the detailed surface processes on Venus, to which extent it is still active nowadays, and so on. It will be launched in 31 and arrive roughly 2 years later at Venus in 2033-34. And now going much further in the future, the first large mission in the new program, in the Voyage 2050 program, is kind of a similar concept as JUICE, but for the Saturnian system and including a lander. So the idea is to investigate all those moons around Saturn that may be or are ocean worlds with a subsurface ocean, and at the end to land on Enceladus, which has been discovered by Cassini to have active plumes, so essentially materials that may come out of the subsurface oceans that can be investigated. And this is a little bit more further in the future. So taking the middle graph here, it's foreseen to be launched in around 2042 and then arrive in Saturn and do its investigations in the 2050s. So it's really a mission in preparation for the next generation of scientists, at least if you are my age. I now go to the robotic exploration program. So essentially, this is a program to not so much with a focus on the scientific investigation of the Moon and the Mars, which is also done, but also an exploration with a view on human presence and establishing human presence on the Moon and getting humans to the Mars. And what is shown here is essentially the interconnection of all this from the utilization of the space station to lunar missions to the Gateway and to the future lunar space station, and the future lunar landers up to a lunar habitat in the future, and then later to go first robotic to Mars, maybe have a Mars sample return in cooperation with NASA, and for future human exploration of Mars. I should say that this program is a little bit more in flow than the scientific program, so I will sketch it out a bit more. So for the Moon, it's foreseen to contribute the European Service Module to the Lunar Gateway, which is essentially a space station in orbit around the Moon that is supposed to be started towards the end of this decade. Then there is the Lunar Communications Program, which is essentially trying to get kind of a global navigation system for the Moon, with the first precursor mission to be started this year, the Moonlight mission, and then it will be followed in the Lunar Pathfinder mission and the Moonlight program also towards end of this decade in the early 2030s to really have a communication structure on the Moon that should help for lunar exploration. Furthermore, the so-called series of Argonaut lunar landers is currently being built, so they will be able to get up to 1.5 tons of payload to the Moon. And the first one is foreseen to be launched in 2030, also with a focus on supporting the communications infrastructure of the moons, but further ones will have different type of payloads and also bring scientific payloads to the moon. Coming to Mars exploration. So the program also, due to the situation with the possible change in the NASA program, this is a little bit more in the flow. So the certain elements are the trace gas orbiter, which has been launched in 2016. It is still getting atmospheric data, atmospheric spectra and surface data from the moon. In the ExoMars program, the Rosalind Franklin rover will now be launched in 2028 with a view on looking for probably extinct life or biologic activity on Mars, with the first time a deep drill that will be drilled 2 meters into the Martian surface. And further in the future, the Mars sample return is currently a little bit uncertain what the future will be, because of the situation also that it is redefined at NASA. And more in the next decade, essentially large electric propulsion spacecraft are foreseen to be sent to the moon also, or to Mars also, with the opportunity to get bigger payloads there. How much time do I have? Okay. Last program relevant here, last but not least, is planetary defense, which is a little bit the realization from the last decades that the risk of an asteroid impact is kind of a low likelihood catastrophic damage risk. So it's a catastrophe that doesn't happen frequently, but it's something where it's good to be prepared for. And it turns out we are probably the first generation who is capable of preventing an asteroid impact should it be necessary. So one focus of this is in observing missions. So of course, to do something about it, one needs to find them first and track them first to know what the risk is. And there, ESA has the Fly-Eye telescopes, which are essentially in the discovery. The idea is to discover the small objects of 20 or 30 meters or so size at least days to weeks before, which of course doesn't allow deflection, but doesn't allow some civil defense against the object. And then the NEOMER missions, which together with a corresponding NASA mission will find those asteroids that arrive relatively close in angle from the sun, which are difficult to be detected by other surveys, and which will help to detect nearly all of the asteroids in the science range of a couple of 100 meters. And I'll come to this in a minute. We will take advantage of the opportunity given by asteroid Apophis flying by at a bit more than 30,000 kilometers inside the orbit of geostationary Ceres to Earth. So the first ESA planetary defense mission is Hera, that was launched in 2024, and it's essentially looking at the outcome of NASA's DART mission, which impacted Dimorphos, the moon of asteroid Didymos, in 2022, and now Hera goes there, and it will essentially look at the outcome of the impact. Hera is taking 2 CubeSats with it, one you've called Juventus, the other Milani, and just to mention, the main instrument of Milani is the aspect spectrometer that was built here at Aalto University. So the Hera mission profile, just March of this year, we flew by Mars, and arriving at Didymos, it essentially follows in terms of navigation the example of Rosetta, but with more onboard autonomy. And after a close inspection of the asteroid, both with Hera and with its 2 CubeSats, the CubeSats at the end will land on one of the 2 asteroids, and actually the end of mission scenario for Hera is still being decided right now. But arrival is October, November this year, and the nominal mission goes 7 months and maybe extended a couple of months. Finally, there's the Apophis opportunity, and there we have as a next mission in the planetary defense program, essentially to see which changes will happen when Apophis flies by 30,000 kilometers from the Earth. In the previous session, we had some predictions from it. So we will arrive with Ramses 2 months before the closest approach to be able to have the before-after comparison. In case, of course, one is the change of the spin state and orientation. And also to see, we learned that we probably won't be able to measure the deformation, but we will have a seismometer on one of the CubeSats that will be able to measure any tidal effects that produce seismic waves. And we also look for anything moving on the asteroid surface with decimeter resolution. And we will also look into the interstructure and the changes with the radar on one of the CubeSats. So it goes there with quite sophisticated instrumentation to see what changes during the flyby. And thanks for your attention, and I'm happy to answer questions.
Thank you very much. Michael Küppers, mission scientist from ESA. As you see, it's absolutely fascinating. We have life on Mars, asteroids, Jovian system. Do we have any question about the coming mission? I would like to ask, do you think we are going to find life or fossil life during the next decade?
Life anywhere, you mean?
I mean, outside of the Earth's surface.
Yeah.
Asteroids?
No, outside, yeah. Difficult, I mean, for Mars, it's difficult to say. I mean, one interesting question for me is always, what would we need to find to say that there is no life on a given object?
I agree, because there might be something else which we haven't seen. So it's sort of proving it false is really, really difficult. But absolutely wonderful fleet of really impressive missions on the science side to the planetary space. And so do we have now a question? If no, then give a big hand. Michael Küppers from European Space Agency, a mission scientist. And next, European Space Agency is doing very good job in many fronts. And as we were learning here, we don't have only science missions, we have weather missions, Earth observation mission, communication missions, navigation missions. So the next up is coming the brand new and very impressive in the Copernicus remote sensing fleet mission. Marco Celesti from ESA, he's a mission scientist in Copernicus program in many optical instruments working, and he's going to tell about the new missions, FLEX and CHIME, which are in the spectral and optical region. So Marco, the floor is yours.
Thank you very much, and welcome everyone. Thank you for the invitation. My challenge is a bit more confined to indeed a couple of missions only, and let's hope you will find it interesting. Indeed, ESA is developing, in terms of Earth observation, a number of programs which you might be familiar with, some more related to science exploration, which are called the Earth Explorers these days, the Copernicus missions, operation Earth observation, monitoring for all sorts of surfaces and applications, and then the meteorology program. I will start with one component of the future Copernicus, which is CHIME indeed. CHIME is building on a legacy of multiple imaging spectroscopy missions which are been flying since a number of years, thanks to the work and cooperation of national space agencies like ASI, the Italian Space Agency, the DLR, the German Space Agency. And imaging spectroscopy has proven to be an extremely effective tool for a number of applications when it comes to monitoring vegetation traits, soil composition, mineral mapping, and also abundance of these minerals on Earth, on the Earth's surface. And as usual, the advantage of remote sensing is that it provides, let's say, a global view, but with a very high, relatively high resolution, right? And CHIME will build on this experience by adding a monitoring component to that, focusing on a number of primary applications related to what we've seen, so soil, vegetation, and mineral raw materials exploration mainly, but without forgetting all the secondary applications which will be enabled by the global carpet mapping monitoring capabilities of CHIME, linked, for example, to cryosphere, biodiversity, water quality monitoring, and even atmospheric compounds. When it comes to having, let's say, an idea of what CHIME will look like, we'll have 11 days repeat cycle with and revisit with 2 satellites in place, thanks to a swath of 130 kilometers, and everywhere on Earth where we observe, I will tell you in a minute. We will observe with 30 meter spatial resolution over the spectral range of the visible near infrared shortwave infrared between 400 and 2500 nanometers. We sample with a constant spectral sampling interval of 8.4 nanometers and also a very stable full width alpha maximum across the spectrum of about 10 nanometers with stringent, let's say, requirements on image quality. On board, we have a quite powerful computer doing real-time analysis on the data that we collect, particularly to detect cloud. So we have a machine learning support vector machine algorithm which detects clouds in real time, create a cloud mask, then this mask is eroded, let's say, to ensure that we only select thick clouds in that, and we apply selective compression, so very high lossy compression over these clouds which are not of interest, let's say, for the mission. And in this way we preserve very high quality control near lossless compression for every other surface pixel, which is the core interest of the mission. This is absolutely necessary because the amount of data that we are acquiring and dumping from this mission is massive, really massive, at least compared to other Earth observation missions that we have running. We are testing all that in an end-to-end simulator system, basically where we are capable of starting from realistic or not, depending on what we want to see, variabilities of surface properties, so geophysical properties, which then we can simulate surface reflectance, propagate to top of atmosphere, convolve these highly oversampled signals to with CHIME spectral response functions and an instrument module, and so generate, let's say, top of atmosphere representative spectra from CHIME and images from CHIME. And then we have the full level 1 and level 2 processing inside the end-to-end in order to get back to the surface reflectance and geophysical properties and see how good we are doing that before launch, basically. In terms of level 2 products, besides surface reflectance, which is our core operational level 2 product, we are also prototyping a number of higher level products linked to our main applications and main objectives. And this is a very short subset of what the communities are already preparing for CHIME in terms of exploitation, and this is being done in a parallel activity or a set of parallel activities, which is called Sentinel User Preparation Programs, where 20 application projects have been selected covering a number of high priority applications. But I'm sorry, the text is very small, but if you check the slides afterwards on your laptop, you will see that these high priority application domains really span across a lot of domains, of relevant domains. And CHIME, just to give you a figure, is in 17 out of these 20 proposals. So the use of CHIME is really critical and is being prototyped for a very large range of applications, so not just related to vegetation or agriculture mapping even. I want to point out that we are, besides the fully simulated activities, we have also campaigns. So we have had lots of campaigns, airborne, in situ, and satellite-based campaigns. And the most recent one was going on this summer in an agricultural area close to Munich. In principle, the idea is to collect CHIME-like surface reflectances oversampled in time compared to CHIME, because for the first time, CHIME will provide time series, 11 days time series, a la Sentinel-2, let's say, in terms of consistency of the repeat with a image quality which is higher than what we currently have from sparse observations from the satellites I've mentioned before. And so we need to see how to use basically this high frequency or relatively high frequency of temporal data for our applications, and for that we run these campaigns. What I want to point out is that all data will be available through the ESA campaign portal hopefully soon. So if you're interested in having a look, there is a large number of collocated observations with ENMAP, PRISMA, DASIS, airborne, and in situ measurements as well. So here are a few links, let's say, to know more about CHIME, and thank you very much for your attention. I will jump to Flex straight away in the interest of time. So Flex, you see, is part of the more scientific exploration program of ESA Earth observation, and it's the 8th satellite mission selected in the Earth Explorer program, and it's scheduled for launch starting 1st of September this year. And so Flex has the objective, quite ambitious I would say, of retrieving full spectrum vegetation fluorescence and also other products and metrics related to the energy dissipation, regulated energy dissipation of vegetation, in order to quantify actual photosynthetic activity of terrestrial vegetation. This at a global scale to provide indicators for vegetation health status, but also for monitoring, let's say, at very local scale, these aspects in order to enable, let's say, precision agriculture, monitoring and farming in the future. What is solar-induced fluorescence? Maybe some of you might have heard about it, but basically during photosynthesis, when the solar light is absorbed by plants in order to produce, let's say, sugars and using and oxygen, using CO2 and water, there is a faint, very faint signal which is emitted in the red and far red, which is related inherently to the functioning of the photosynthetic machinery, basically. And this is the only visible signal we can have of photosynthesis. And visible, I mean, even with naked eyes in the right conditions. So if you were to look at night and under specific illumination conditions of the plant and maybe with the support of some glasses, special glasses, you would see the plants glowing red. They always, all the time, make this faint glow, but the problem is that the amount of light which is reflected by the vegetation in the wavelengths which are visible to our naked eyes is much, much stronger than fluorescence itself. But it's always there. So when you go outside and you see a tree, even in this, let's say, cloudy sky, plants are photosynthesizing and they are emitting fluorescence all the time. So being a radiance flux, we can sense it also with remote sensing, by means of remote sensing measurements. And so we have to take care of a lot of things happening. So the sun goes through the atmosphere first, then hits the surface, most of the light is reflected, then some is absorbed, and fluorescence is emitted on top of that. Then it has to go through the atmosphere again, and finally, eventually reach our satellite observing system, 812 kilometers up there. And if you don't see it with your naked eyes, imagine how difficult it is to sense it from 800 kilometers. It's a real challenge indeed, but when we have the information on both peaks of this peculiar shape of the fluorescence, which is emitted in the red and far red wavelengths, we are able to understand the functioning of the main photosystems which act in the two photosystems which are responsible for photosynthesis ultimately. And in order to do that, we get a help from the atmosphere actually, because there are two bands where the solar light is absorbed heavily in the atmosphere, which are, there are others, but the two that we conveniently use are the O2 absorption bands, the O2A and O2B, which are placed relatively close or to the peaks of the fluorescence, or in a position which is helpful for its retrieval. And if most of the incoming light is absorbed in these wavelengths, it means that also there is no or very little reflection back from the vegetation. So the ratio between the reflected radiance and the emitted radiance, so fluorescence, is minimized in those spectral regions. The spectral regions are tiny and hard to measure, so we need a dedicated spectrometer for that, basically. And the challenge, of course, is that in our way up to in the atmosphere, the signal is also reabsorbed. So we have to take care about the atmospheric absorption and scattering during its way down from the sun to the Earth's surface, and also of the radiance from the surface to the way up to the satellite. In order to enable this very high detailed characterization of the atmosphere, FLEX is not enough. So we fly in tandem with Sentinel-3, and Sentinel-3, particularly ALCHI and SLSTR, two of the payloads on Sentinel-3, provide us with additional measurements to characterize the atmosphere, and also other land surface properties which are complementary to what we can get from FLEX in terms of fluorescence and dissipation-related metrics. We fly in a relatively tight tandem, so the temporal co-registration requirement was between 6 and 15 seconds between the two satellites, because clouds move and the atmosphere might change in the meantime, so we want to be very close and have the two measurements very close in time. Both the tandem, let's say, strategy and the orbit control to reach it has been absolutely confirmed. There's no concern with that. And as I mentioned, anticipated, FLEX will be launched together with Sentinel-3C on a Vega C launcher from Kourou, Guyane Space Center, starting 1st of September. So this is basically the view, the combined view of the spectral coverage of FLORIS, which is the spectrometer on board FLEX with its high resolution and low resolution components, and SLSTR and ALCHI. So you see that we have a very high, very detailed understanding of the oxygen absorption bands with FLORIS HR, then a larger coverage from 500 to 780 nanometers with FLORIS low resolution, which is still an incredibly resolved spectrometer. We're talking about 2 nanometers spectral resolution, so there's nothing up there at 300 by 300 meters spatial resolution whatsoever. And then we have ALCHI and SLSTR to complement spectral coverage. We have also a number of unique proposed products, which I don't expect you to read now, but just to tell you that we are really heavily preparing both a suite of level 1 products combining FLEX and Sentinel-3 together on the same grid to maximize and ease the exploitation by the users, but also on level 2 products linked to reflectance products, fluorescence products, and also advanced photosynthesis products, which we are prototyping, and we will definitely have to consolidate while we have the FLEX measurements in place. We are working towards a global network of in situ measurements for FLEX. We have a reference in situ system which is called FLOX, but there are also other measurement systems for fluorescence and reflectance, which we want to include and use and maximize the usefulness of. You can see in the map on the bottom right that basically these systems already have quite a wide coverage, from a global perspective, and the numbers hopefully will increase in the coming years. This network is community contributed, so if a research group or a scientist has an instrument which is capable of measuring reflectance and fluorescence in situ and wants to contribute to this network, then basically similarly to other networks, this measurement will be collected into a large common database and then under certain terms and conditions shared with the global community. This will be useful for the validation of Flex products, starting from the commissioning phase, but also, I believe, from a larger perspective in combination with ecovariance measurements and other remote sensing products for understanding global vegetation patterns and dynamics. So we have, in terms of Flex validation, I think it's my last slide, we have an announcement of opportunity again for community contribution for the Flex calibration and validation activities. The second round of submission is open until the 1st of February. If you're interested in joining, let's say, the calibration and particularly validation activities for Flex, starting from the commissioning phase and then the operational phase, please have a look. There will be another round opened shortly after. Basically what we do is we close on the 1st of February, we evaluate the proposals, and then we reopen after a while. So don't worry if you're interested, but you can't make it for the 1st of February. And then a few additional preparatory steps. We have a workshop in Bonn, 3 to 6 of March. The registration will open also early February, where we really cover all the aspects from mission preparation to science and validation. I mentioned already this international network, and also we are going to publish updated versions of our validation plans, also of protocols, to guide the community into these validation measurements very soon. With this, I thank you very much, and this time for good.
Thank you, Marco Celesti. So don't leave yet, we have time for a couple of questions. While we are still looking for life on Mars or somewhere else, we are able to characterize the very engine of the biosphere, which is the photosynthesis, with the new missions very, very accurately. So we have a question back there. The microphone is arriving.
I have a question for Chaim. You mentioned an AI computer. Is that actually an AI, or is it just a reconfigurable computer that's optimized with an AI that's running on the ground?
So it's you will forgive me if I don't have the exact technical specification, but it's embedded in our data processing unit, and I can provide you more information offline if you wish. What we do is in real time we process basically chunks of the entire SWOT that we acquire with the 3 spectrometers which build up the SWOT, and in real time we assess, we process with a support vector machine based on 7 bands and 5 combination of bands. If a certain pixel, each pixel is to be classified as cloud or not.
Okay, that's the cloud identification algorithm. But is this algorithm updated on air or so in space?
Okay.
In space based on the data that's coming in, or is it optimized?
I understand your question now. Sorry. No, the algorithm is trained on ground, and then the coefficients are uplinked basically to the satellite.
So then it's not an AI, it's just a reconfigurable computer. So that was the question, because there's a lot of discussion on AI in space, but then you need a big data center and a lot of data sets and petabytes of data that need to be processed to train the AI. So that's why I was triggering on the AI computer, let's say.
Yeah.
Thank you.
All right, any other questions? If no, then thank you very much, Marco Celesti. One more applause. Mission scientist from European Space Agency. And next in our program is lunchtime. I remind everybody we have 2 restaurants. We have also Mezzo, which is a wonderful salad bar. I recommend it very highly, especially today where there are less queues. And see you in the afternoon sessions. We have space business coming. We have more planetary, lunar, different kind of things. So full program will end around 5 o'clock. So welcome back.
Here. Then is Adam Mitchell possibly here? Nice to see you, Adam. Would you be able to present 15 minutes beforehand your own presentation, since the one Elena, who should be now presenting, is not available for now? Excellent. Let's get you all mic'd up. And backstage you can put Adam's presentation to the big screen in a couple of seconds. We're going to start off with Adam today, and we're going to just look and hear a presentation about understanding the atmospheric effects of spacecraft re-entry. I think, thinking about yesterday or the day before, these days topics are even more sci-fi than I would have expected, and it's nice to see this kind of in-depth technical presentation about topics we are accustomed to seeing in sci-fi movies and TV shows and books. But Adam, once we have you mic'd up, you can present whatever you want to say. So let's welcome Adam with a round of applause to the stage. Welcome, the stage is yours.
Okay. Is this on? Thank you, everybody. Can you hear me? Perfect. So, my name's Adam Mitchell. I'm here. Okay, thank you. So my name's Adam Mitchell. I'm from the European Space Agency. I'm a space sustainability engineer, and I'd like to talk to you about understanding the atmospheric impacts of spacecraft re-entry. So I'm working as part of the ESA Green Agenda. So it's a program mobilizing all of ESA, the space sector, to contribute towards the climate neutrality of Europe while increasing competitiveness. It's about increasing the contribution of space projects to the sustainable development of society, but while it's also decreasing the environmental impacts of the space sector. This is really focusing on 5 main areas, and I'm interested in the middle one there, reducing the environmental impact of space systems along their entire life cycle. I'm focusing on the end of life of satellites and how they re-enter the atmosphere. Now, the current situation in space is approximately you have 54,000 objects greater than 10 centimeters, around 14,000 active payloads, so 1.2 million objects from 1 centimeter to 10 centimeter, and 130 million objects from 1 millimeter to 1 centimeter. So to try and make space more sustainable, we're implementing certain policies, because we are on our way to a collision cascade known as the Kessler syndrome that could render low Earth orbit unusable. So we need to make space more sustainable. We are reducing the post-mission lifetime limit from 25 years down to 5 years, with some more strict restrictions on mega constellations, even down to 2 years. We are investing in active and passive deorbiting, so capturing satellites and burning them up in the atmosphere. We are designing satellites to demise, but high vaporization at high altitudes. I also put very low Earth orbit in there because that will become very populated. The question is, how far are we from the in-space circular economy, manufacturing in orbit, recycling and reusing and relaunching from space? the main point of this slide is say, okay, making space more sustainable has consequences. So back in 2023, I initiated a working group with the European Space Sciences Committee. This is with NASA, NOAA, COSPA, DLR, the COGNES, also participation from the United Nations and the European Commission. The working group identified scientific knowledge gaps, defined research that agencies can fill, also to foster collaboration between the different stakeholders. We ultimately developed an atmospheric roadmap built on 3 pillars: field data collection, advancing ground testing facilities, and integrating those results into chemistry climate models. The working group has also built a white paper of urgent recommendations focusing on atmospheric in situ measurements and improving the ground testing facilities. So this white paper that will be released in a couple of weeks was put together with the participants of the atmospheric workshop in ESTEC in September. The workshop focused on field measurement campaigns and understanding how to detect and analyze aerosols from launcher and spacecraft-derived particles. It also, we were looking at the chemistry in terms of metal oxides, black carbon, and how it interacts with the background stratosphere and the mesosphere, including the potential to catalyze ozone depletion and cloud formation. So this white paper, as mentioned, will be released in the next couple of weeks for you to look at. Now, what is the current situation? The natural input for meteorites is around 12.4 kilotons, roughly, per year. The space waste in 2019 was about 0.89 kilotons re-entering. That's steadily increasing to about 2.3 to 2.5 kilotons per year, and it's going up. But it's not just about mass, it's about chemistry. It's about understanding the materials that you're injecting directly into the stratosphere that haven't been there before. Aluminium and copper are already well above the natural input from meteorites. Now here, I just want you to focus on the 2 red boxes. The rocket going around the middle is Draco, and the Draco is an ESA mission that will help us understand the fragmentation of satellites. But fragmentation, when a satellite ablates, the difference between a material that fully vaporizes versus the material that forms coarse fragments is the first order of uncertainty that controls atmospheric impact. Anything larger than 1 micron will sediment rather quickly through the atmosphere. Then it becomes an issue for the land or the sea of where it deposits. But when we say a satellite, say 50-60% of it vaporizes, it doesn't just vaporize. The metals and the halogens cool, they recondense in the wake, and the surrounding air oxidizing, hydroxylating, and nucleating as nano-sized particles that can grow by condensation and coagulation. These long-lived submicron aerosols, which are less than a micron, are the most concerning for ozone chemistry and radiative effects because they persist for months or years into the stratospheric aerosol population. It is these small particles that provide services for ozone depletion and polar stratospheric cloud processes. Now, the difference between space debris and the natural impacts, you can't really compare them because spacecraft are much larger, there's more complex ablation, lower temperatures and lower speeds. Ultimately, they encounter completely different atmospheric conditions. It's important to remember that the chemistry of any element will change as a function of altitude. Now, what research has been done? There's been an excellent work by Daniel Murphy in NOAA. He, in 2023, flew the NASA aircraft with the Sabre flights in Alaska, and at 19 kilometers, he sampled 500,000 particles. Of those particles, 10% of them contained metals from spacecraft re-entry, which is a remarkable number considering the number of re-entry events. There was lots of dispersion. Now, every 6 months, the mesosphere is flushed into the winter polar stratosphere.
And this is where these particles sediment down and they encounter the sulfate layer where they're encapsulated in sulfate. So what is ESA doing about it? In the red box, we united two activities, but I just wanted to introduce you to this platform. It's the Open Space Innovation Platform. If you haven't heard of it, you can apply it at any time. You can do different implementation schemes, studies, early technology projects, or even co-sponsored research. Please have a look at it online. This is the platform that enabled us to do further research into this area. But I just wanted to also mention, before we go into these two activities, the impact of new materials. I see a lot of people talking across Europe and in Japan about using wood for wooden satellites. Before you do that, you have to understand the combustion products and the incomplete combustion products that are left in the atmosphere, in the stratosphere, the black carbon and the soot formation, and how that interacts as it sediments, before you start implementing these on a much wider scale. It's frozen. Okay, so one of the first activities we initiated with OZIP was a facility to specifically look at the vaporized fraction. So this vaporizes different materials in irrelevant stratospheric and mesospheric conditions. Now we're looking at aluminium alloys because they are the majority of the structural satellite. We're focusing on 6,000, 7,000 series and looking at what point the major alloy constituents evaporate. And one of the early indications of this facility show that the primary atmospheric product observed is aluminium hydroxide rather than alumina. This has significant implications because the aluminium hydroxide is far more likely to release the chlorine from the hydrogen chloride reservoir with possible implications as the chlorine then goes on to deplete ozone. So within this facility, we are testing all materials to specifically look at the vaporized fraction. We are then combining it with the other ground testing facilities, such as the plasma wind tunnels. The plasma wind tunnels really focus on demise, how these materials are fragmenting. But now, when we combine these two facilities, we have a full picture from melting, formation, to fragmentation, evaporization, and oxidation. Now, this is work done by the IRS in Stuttgart. We're testing all different types of electronics. Here, they're focusing on the particle size, particle fragmentation during re-entry, but I'm interested in the vaporize. Are we seeing aluminium hydroxide? What's in the gas phase as it's ablating? We then move on to the modeling. So the results you get from those facilities, you put them into models. And what you need is the injection rates of different metals as a function of height, latitude, and time, and the chemistry of the formation of these metallic particles and the reactions with HCl. We also need a global chemistry climate model. Here we are working with the University of Leeds and Professor John Plain. We put in the results from the facility into WACAM4. That includes 66 different chemical species, including the sulfur-containing species. And this is important because on the left there you see the orange, if you look at the orange particles, they are slowly sedimenting, and as they sediment, they're encapsulated with the sulfate. This sulfate is potentially deactivating or passivating them from further reactions. It's a complex process that needs much more attention because on one hand, it can deactivate them, but on the other hand, you're increasing the size of the chemically reactive sulfuric acid. And therefore, the overall net effect needs to be studied. In the runs, this is with today's aluminium only. We were looking at the ozone depletion. This is negligible when the space debris particles are deactivated by the sulfate. But as soon as you remove the sulfate, if you remove the sulfate and the deactivation layer, then the ozone depletion becomes significant. This run is with today's aluminium only, but if the sulfate was not deactivating the aluminium from reacting with the hydrogen chloride layer, the ozone depletion becomes significant. And this is why we need a lot of attention and understanding that chemistry of how these metal particles, as they sediment, how they react with the sulfate layer. Now there's different campaigns that we are initiating. Here in the stratosphere, we're looking at a potential vehicle, the Zefler Auto. It's 100% solar powered. It can launch really up to 22 kilometers, and then it carries a 6 kilogram payload. But the idea here is to capture the aerosols and bring them back so we can study the composition and morphology of the space debris within the lab. We're also initiating several flight campaigns, but these can go up to much higher altitudes, up to 40 kilometers. Here we will sample between the sulfate layer and above the sulfate layer to see how the sulfate is actually chemically aging the metal particles and if it is deactivating them. If you want to go much higher, then there has been some campaigns already with sounding rockets up to 80 and 100 kilometers. But you have to be careful with sounding rockets because of the speed at which you sample the particles. You can effectively damage what you're collecting. There are other emerging platforms like Dawn Aerospace, a vehicle that can sample at a much slower speed. So at the apogee, it can slow down to about 50 meters per second. In the red box at the bottom, I highlight there's a new campaign on OZIP coming up with new ways to sample the mesosphere and the stratosphere, new payloads, new sampling, new sensors. So look out for that campaign. Oops. This is just a summary, but I would like to highlight to you there is a new SLICE network. This is from the Marie Curie Fund, got 5 million. It's a doctoral network with 18 PhDs currently open, and the deadline is the 31st of March. Please have a look at the link if you're interested in this project. Thank you.
Thank you for presenting. Thank you.
Do we have any questions
from the crowd regarding this topic?
There's one. Can we get the microphone over there, please? One in the center, and then Jan would like to ask something as well.
I follow on space debris. We had a call for its remediation and recycling. In your opinion, I think the pollution of the atmosphere from space debris is a major issue. In your opinion, what type of technology shall we look and select in project low TRL? Whether ones which burn in the atmosphere or go into gravity orbits? What is your recommendation, having in mind the researcher?
We discussed at the workshop. We don't have to burn satellites up in the atmosphere at end of life. There is another way. So there's a lot of work going on in manufacturing materials and in microgravity and the pharmaceutical industry. Companies like Space Forge and Atmos can use inflatable accelerators or decelerators as they re-enter. You can bring back sensitive payloads from microgravity and land them close to coastal regions and recover these materials. This is early TRL, but I think in the future, if we wanted to bring back satellites at end of life, recycle the materials, reuse them, we technically can.
Thank you. There was also a question. 2 more questions, actually.
Okay, thank you very much. Johanna Tamminen from Finnish Meteorological Institute and also a member of the ESSC. Very interesting presentation. I was wondering, there are observations like air cores, for example, from Sodankylä, Lapland, which are instrument tubes that are taken with a balloon up to the stratosphere, and then the tube fills in with the air while it's descending. with a parachute, and this air is collected regularly, for example, in Finland, in Sodankylä, high-latitude site, perhaps once a month, something like that. And perhaps these observations could be also used for this purpose. They are normally used for analyzing the atmospheric profiles of greenhouse gases.
Yeah, exactly. I spoke to Serge and Sean David, and they mentioned it as Air Core to me. It's part of the white paper that we do mention it. But we're working with Sliman Becky as well from CNRS, who's developing new payloads for stratospheric air balloons to do sampling. But any sampling of the atmosphere we are very much interested in.
Hi. So my question is about the data collection from the upper atmosphere and from the stratosphere as well. So you mentioned the balloons are used or can be used, I missed that part, but what is the need currently about that data which further research can support in the future? Like, is it the amount of data, or is it maybe the quality? So what is missing there?
The collection of materials in the atmosphere, we need to, this will help develop our models. So we're using balloons, sounding rockets to try and get as much data as possible to understand the composition, the morphology, because these have significant implications on, for example, cloud formation. Once we can get these particles, nano-sized, micron-sized particles back to the lab, we can better understand how they react with sulfuric acid, how the ice nucleation processes for cloud formation. That will help us improve the models and get them correct if we're to scale this up.
And can I say it is the amount of data? Is there a limitation, or what you have with balloons is already enough? So what is missing? Is there anything missing there?
We are missing, the only study they specifically related to spacecraft re-entry was that of Daniel Murphy. He did an excellent analysis of the aerosols. There isn't much out there analysing, specifically looking at space debris in the upper atmosphere. We need more, which we are initiating balloon campaigns targeting certain areas, especially the polar regions, to look for this debris.
Okay, thank you.
We have further questions round. If not, one more round of applause for this presentation. Thank you. We actually have two presenters in this track have called in sick, so we're gonna actually have about 15-20 minute pause for now. You have time to go get some coffee, go to the bathroom, or even take a nap if you wish. So we're gonna come back in exactly 20 minutes, and our next presenter will be Rahul, who will be presenting online, so we're gonna get the Zoom all fixed up before that. So if you want, go get some coffee, go take a break, we'll be back soon enough. Let's hope the online presentation is going to go okay as well. We have Rahul Thakur online presenting us about resonant harmony, how leveraging orbital resonance in different kind of things. I don't actually understand any of this, but I believe Rahul can explain this whole topic way more in depth. So let's get Rahul from online to present to us with round of applause. Thank you. Couple of things on the technical side, and then we should be all good to go. Fully. Thank you. This is a good reminder for everybody when you're thinking about, I'm going to be presenting at a conference and I'm going to do it remotely from home. Please don't do that. It's easier and more fun to travel to these places and present on site.
Yeah, I can hear you. Uh, Good afternoon, everyone. My name is Rahul, and I'm an independent researcher from India. And this work is co-authored with my best friend, Ridhima Sur, who unfortunately could not be here with us today. So the title of this talk is Resonant Harmony, which is leveraging orbital resonance maps to architect safer, smarter, small satellite constellations. The core motivation behind this work is a shift in perspective. The most constellation design workflows, it's where the orbital resonance is treated implicitly as a nuisance, something that introduces long-term drift, unpredictability, or instability that must later be corrected operationally. What this work asks instead is a more fundamental question. What if resonance is structured in such a way that while designing, we do not design stuff around it, rather with it? And this is not a proposal to abandon the collision avoidance or traffic management, but rather it is an argument that long-term orbital dynamics should be treated as a first-order design constraint and not an operational afterthought. The thesis of this talk is that resonance, when properly mapped and understood, can act as a stabilizing scaffold for constitutional geometry, reducing the long-term drift and cumulative risk exposure. Everything I'll show today follows from this framing. To understand why this matters, we need to look at the current state of the low Earth orbit. LEO is transitioning from a sparsely populated environment into a densely occupied one. Current projections suggest that tens of thousands of satellites will be operational within the next decade, primarily driven through the large commercial constellations. Most mitigation strategies today focus on short-term collision risk, which are conjugation assessment, avoidance maneuvers, and real-time tracking. These tools are necessary, but they are fundamentally reactive. What is less frequently addressed is that structural evolution of constellations over the years. We see that small secular effects such as precisions, plane drift, phase decoherence accumulate quietly, altering the geometry long before conjunction alerts are triggered. From a modeling standpoint, this distinction is important. Many long-term risk drivers are deterministic, and the consequence of orbital mechanics, which are not random events. In this work, we therefore explicitly define our scope. We do not attempt to predict the individual collision probabilities or replace operational conjugation screenings. We ask, how does constellation geometry evolve under known perturbations, and how does that evolution influence long-term exposure to hazardous configurations? Orbital resonance is often described qualitatively, but rarely treated as a design variable. In practice, resonance arises from well-characterized sources, such as Earth's oblateness through the J2 term, nodal and epicidal processions, and the lunisolar perturbations. All these effects are deterministic and continuous. A key observation motivating this work is that resonance is not rare or pathological. It is almost everywhere measured. For almost any altitude and any inclination in LEO, some form of consumability or near consumability exists. The problem is not resonance itself, but the misalignment with it. I have designed this whole project into 3 different models, which I'll be talking about in the coming slides. The gist is, in the first model, that is the model A, I'll design the orbital maps, which will be quantified by computing secular drift rates across altitudes and inclination grids. These include RAN drift, argument of perigee drift, and ground track consumability metrics. What emerges is a structured resonance landscape. As you can see in the plot that I've put on this slide, the drift score, we can see that based on the inclination, how does it affects uh, the drift score. Most important, these structures persist across perturbation models, even when I'm considering third body in J2, third body in high drag, third body in moderate drag. All these things are still under the influence when it comes to designing these orbital resonance maps. And they do not vanish suddenly without any reason. They will always be there and they will always account for certain actions that we can take in the future. As I said, that I've designed this whole project into 3 different distinct modules. Mainly, they are the orbital resonance mapping, the resonance-aware design, and risk analysis. The first contribution is orbital resonance mapping, which systematically identifies stable, resonant, and transitional regions in orbital parameter space. The second is resonance-aware constellation design, where these maps are used to guide inclination section, plane spacing, and rand dispersion. And the third is the risk analysis framework, which is centered on resonance exposure index, which quantifies long-term geometric risk accumulation. This is the metric that I've reduced. Like when I ran the simulations, I saw that 40% risk reduction is measured, which is related to the Walker delta baseline over a 10-period propagation period. And with that, every output metric has a physical interpretation, and every design choice can be traced back to orbital dynamics. This slide shows overall framework both conceptually and computationally. The code base is structured into 3 primary modules, as I've been reflecting through the previous slide. But in this slide, we'll go into much detail on what exactly I have done in all these 3 modules. Module A performs orbital propagation and resonance analysis. It ingests grids of altitude and inclination, propagates test orbits under selectable perturbation models, and computes drift rates and coherence metrics. Module B constructs constellation geometries. It's basically it's based on vocal data baselines and resonance-aware designs under align the same generator, ensuring identical satellite counts and coverage assumptions. Module C evaluates risk metrics using propagated constellation states. In this module, I have put on the layers as perturbation model selection, time horizons, threshold definitions, and output resolutions. This structure allows experiments to be reproduced and extended without modifying core logic. Coming on to the orbital resonance mapping, this is the foundation of the framework. We begin by propagating individual test orbits across grid of altitudes and inclinations. Propagation is performed over multi-year horizons to capture secular effects. The modeling approach is incremental. We start with only J2 dynamics to establish the baseline structure, then introduce lunisolar perturbations, and finally the atmospheric drag in 2 components, one with the moderate drag and second with the high drag. This staged approach allows us to test which resonance features are robust and which are sensitive to modeling assumptions. For each orbit, we compute RAN drift rate, argument of perigee drift rate, ground track consumability error, and composite resonance scores. In this graph, I have given the example that I've generated as a ground track repeat consumability. The low order consumabilities exhibit 2 to 3 orders of magnitude power lower than PQ error relative to surrounding phase space. Resonant corridors persist under J2 plus lunisolar perturbations, shifting by magnitude of 0 to 50 kilometers in altitude. Coming on to the module B, that is resonance-aware constellation design, we translate resonance maps into actual constellation designs. We compare 2 architectures, a conventional Walker delta baseline and a resonance-aware design that we are proposing. Both share identical satellite counts, plane numbers, and nominal coverage objects. The only difference is, however, on the orbital parameters which we selected. In the baseline case, uniform spacing is applied without reference to resonance structures. But in resonance-aware case, inclinations and RANs are offsets chosen to align with stable corridors identified that in the module A. So here in this plot, I've shown the plane drift error for the baseline and the resonance aware. We can see that in resonance aware, the shear period is 200 day plus, and in the baseline oscillation period is 70 to 80 days. We can see that in resonance, it slows down the shear and reduces the amplitude without active maneuvers. Here in the module C, we'll look at the risk exposure index. RE is designed to capture long-term geometric risk, not instantaneous collision probability. It aggregates multiple physical meaningful proxies. The first that we decided to keep as a baseline is minimum inter-satellite separation. Second is plane drift and shear. And third is symmetry loss over time. Each component is normalized and combined into a single temporal signal. Each threshold is defined conservatively, and REI is evaluated continuously over a period of 10 years. When we compare these baseline and resonance-aware designs, both remain below unsafe thresholds. However, the resonance-aware constellation exhibits consistently lower peak amplitudes and reduced time spent near threshold regions. When integrated over mission lifetime, this results in approximately 40% lower cumulative exposure, as we have seen in the defining slides that I've shown you. Yeah. So this metric comes from the RE. This reduction is achieved purely through orbital geometry, no maneuvers, no traffic coordination, and no reactive control. RE is intentionally not framed as collision probability. It is a structural metric that quantifies how constellation geometry evolves towards or away from hazardous configurations. This is the structural evolution and interpretation slide, where we can see how the traditional design can be evolved to a resonance-aware design. In this baseline design, both we can see that symmetry loss saturates in both cases. In the resonance-aware design, this degradation is delayed by several hundred days. As you have seen earlier, here we can see that it takes 200 days shear period in resonance-aware rather than baseline in the Walker Delta baseline, as compared to 70 to 80 days. From a sustainability perspective, this matters because the risk accumulates over time, and delaying degradation reduces cumulative exposure, even if eventual degradation is unavoidable. I wanted to include a machine learning part where I can see, how can this be included in the pins and every tree-based regressors. So this is just an afterthought or the future work that I can pursue in this research. This is machine learning appears in this work as a proposed extension rather than a core dependency. High resolution resonance and risk maps are computationally expensive to generate. This limits how extensively design space can be explored. Machine learning offers a way to scale this process. Surrogate models can interpolate resonance and RE surfaces, enabling rapid evaluation of candidate architecture. Potential application of machine learning in this field would be continuous interpolation of REI fields, accelerated early stage trait studies, and screening large design ensembles before high fidelity propagation. I've selected some candidate models that we can pursue for these things, which is Gaussian process regression for smooth REI surface estimations, pins for secular drift field smoothing, and tree-based regressors for fast architecture streaming. However, a strict guardrail is maintained where machine learning does not replicate orbital dynamics. All training data is physics derived, and predictions are constrained to physically meaningful regimes. Here, ML is served as an accelerator and not as a decision maker. To conclude, this work argues for a shift in how we approach constellation design. Orbital resonance is not merely a hazard to be mitigated, but a structural feature that can be deliberately leveraged. By embedding resonance awareness into early design, we can construct constellations that are safer, more stable, and less operationally intensive over their lifetimes. The framework presented here is modular, interpretable, and extensible. It is compatible with high-fidelity force models, machine learning accelerations, and future space traffic management systems. Most importantly, it frames sustainability as a design principle rather than an operation burden. And I think that is how I'd like to conclude this presentation. Thank you.
Thank you, Rahul, for this presentation. We are not going to take questions this time because we are running a little bit late from the schedule and we don't want to anger the gods of technology with this Zoom call. But thank you, Rahul, for presenting this topic. Next up, we are gonna move into sustainability. Surprise, surprise in this track. We're gonna discuss about regulation to promote low Earth orbit sustainability. When Michael comes to the stage, I guess you are Michael. Let's welcome Michael to the stage with a huge round of applause. Michael, the stage is yours. Here is the remote. Do you want to use this mic or handheld one?
Try this one? No.
That one? There we go.
So, good afternoon, ladies and gentlemen, and thank you very much for staying up to this point in our turbulent session. So, I will be brief and will provide some behavioral, psychological insights to improve the efficiency of regulation regarding the sustainability of the low Earth orbit. Now, we have seen in the previous presentations that the situation in the low Earth orbit does not look good. It is very congested. This has been deteriorated by the trend for mega constellations. And regarding regulation, at the international level, we do not have any concrete binding rules. We have some non-binding official guidelines, and we have also self-regulation in the form of mainly industry practice. And then we have national rules which vary among states, and the same goes for enforcement of these rules. And regulation without enforcement is a dead letter. So we could say that regarding sustainability, the current situation is largely ineffective, although not totally ineffective. So how could we improve this? We could use some behavioral insights, and as a preliminary point, we should observe that our brain, the human brain, has evolved for survival, not for rational decision-making based on careful data evaluation. We tend to use constantly cognitive biases, which we could define as systematic deviations from pure rationality as is traditionally understood, and heuristics, so mental shortcuts to make a judgment. And these affect both individuals and organizations, including states, since organizations are run by humans. Now, let's see some examples. There is the optimist bias, according to which we tend to underestimate the risks of our own behavior and endeavors. So bad things happen only to others. So nothing bad will happen to our satellite fleet, and even if anything pops up, then we will be able to manage. And this is connected to, among others, the way that the human brain perceives risk. So whenever we evaluate the risk of something, what our brain does is to try to find instances, examples of this risk being materialized. And the more instances it can recall, and the easier it can recall them, the higher is the perceived risk. Another factor for risk perception is conspicuousness. So if we can recall vivid images from relatively recent adverse events, so videos or media coverage, then we perceive the risk to be higher. And since in low Earth orbit, we do not have many accidents, let alone so very, let's say, impressive accidents with extensive media coverage, we tend to think that the risk is low. Then there is loss aversion, according to which potential losses loom larger than potential gains. So, especially companies tend to think that regulation is something negative because it adds costs. Another interesting parameter is the framing effect. So the same piece of information can be evaluated differently regarding on how it is presented. So we may think that a satellite mission is with a 10% failure rate is riskier than a satellite mission with 90% success rate. Then there is the present bias, or what we call hyperbolic discounting, named after the curve that describes the phenomenon. And it means that we tend to prioritize immediate rewards over delayed rewards, even if these delayed rewards are greater. And this has evolutionary roots, because today we live, tomorrow who knows what happens, and we'll see about tomorrow. So let's reap the benefits today. And since humans are social animals, we tend to copy the behavior of others, especially the most influential of us and the ones with the highest social status. So smaller companies tend to copy what bigger companies do, and smaller nations tend to follow the practice of the spacefaring nations. But all this is nothing new, unfortunately. In many industries, for example, in railway, in aviation, in the financial industry, in shipping, we had the same phenomenon. So we had new technologies and new opportunities that shadowed and led to underestimation of risks. So we had minimum regulation at the beginning, let the industry flourish and develop. And then we had grave accidents. Dozens of accidents in railways, which led to more elaborate regulation. We had the Titanic sinking, which led to the Safety of Life at Sea Convention. We had the Exxon Valdez disaster in 1988, which led to measures against environmental pollution. We had many aviation accidents. For example, the 1956 Grand Canyon aerial collision, which led to the reorganization of the entire air traffic control system in the United States. And then we had the stock market crash in 1929, or the 2008 financial crisis. And all these led to extensive and detailed and heavy regulation combined with extensive liability at all levels. So at the civil level, who pays compensation, at the criminal level, and at the administrative level. And history sadly points out that without major accidents, there can be no effective regulation. But it doesn't have to be that way. There are things we could do, mainly at the national level. At the international level, unfortunately, there is no political will for binding international rules. The last time that we had a successful convention, an international convention, was in 1975, so quite recently, where we had the Convention on the Registration of Space Objects. Ever since, all efforts to create new binding rules have failed. So we should focus on national space legislation, and we could introduce, and many countries, among them also Finland, have included provisions on risk mitigation and contingency planning throughout the life cycle of space assets, not only during launch. And this should include mandatory insurance. Now, insurance plays a key role because actually the insurers are the canary in the mine. And they are among the best in spotting risk. And right now, the insurance premiums for launching a satellite into low Earth orbit have skyrocketed because the activity is deemed too risky. And some satellite operators, for example, SpaceX, are self-insured. So mandatory insurance, because insurance premiums can be used as incentives for the promotion of safety, and we should also encourage compliance with international technical standards so that at least at the technical level we have some uniformity. Then regular audits could contribute to compliance for retained licensing and for licensing renewal. We could also think of longer-term incentives for promoting sustainability, for example, tax breaks or technological subsidies. Another idea that can be borrowed from aviation, in which it has been very successfully applied, is to have national databases of accidents and near misses. And these databases can be publicly accessible, albeit with layered access, so anyone can access them, but the granularity of information, the detail of information depends on who is accessing and what they are asking. We could also think of annual public awards for best practices and innovation in order to promote imitation. And awareness campaigns for both stakeholders and the public, in which we could emphasize the risk for losses, especially catastrophic ones, which could affect business solvency. Because if all your satellites in orbit are rendered unusable, then you will probably go bankrupt. We could also reframe compliance costs as long-term investment. And we may also consider highlighting the potential impact on everyday activities, because people tend to care and thus exercise pressure only for things that they affect their everyday lives. And right now, most people think that the use of space is something very remote and exotic, and we'd better get rid of it. But this is not how things actually work. Now, at the international level, as already said, there is no realistic chance for meaningful regulation. However, we could accelerate the work on the development of international sustainability metrics so that everybody is on the same page. We could envisage the use of international databases of accidents and near misses so that examples are readily available, and these international databases could derive data from national databases, but also from international sources. And this has already been applied successfully in aviation. A shared early warning collision avoidance system would also be useful, albeit very challenging in practice to establish. And then we could borrow some ideas from the banking industry, where stress tests are being conducted, and we could use multilateral risk simulations to emphasize the consequences for individual states and operators, especially the biggest ones and the spacefaring nations that have most to lose if the low Earth orbit becomes unusable. So, in conclusion, ladies and gentlemen, the sustainability of the low Earth orbit is crucial. There have been some positive steps. More things can be done, and behavioral science can contribute to this direction. We should keep on trying. Ladies and gentlemen, thank you very much for your kind attention.
And thank you for presenting this topic. Thank you. Do we have any questions from the crowd regarding this? There's one question over there, and I have a question myself afterwards as well.
So you mentioned that international cooperation has been quite hard in the last 50-some years, and Artemis Accord showed that as well. But you said that there would be a possibility to share information, but I'm just wondering, how does China and Russia and possibly right now the United States fit into that, because they are not that willing to cooperate even in space with a lot of other countries.
Yes, you're right. This is very challenging in practice. Even with the registration, registration of space objects at the international level, we have important challenges, and many space objects are not registered because they don't want to register them, or because they are seen as classified, so military assets are not registered, so we don't know, not officially, where they are exactly. But the hope is that necessity will make such information sharing viable, and we could look at the example of aviation. Of course, aviation has a remarkable safety system which has been created, unfortunately, after dozens of accidents. So, again, this is a practical challenge to be quite realistic. I don't think that there will be anything like that, but we might be able to create a critical mass of operators sharing information and states sharing at least some information for the sake of everybody.
Thank you for the question. We have one question over there as well.
So you mentioned the challenges of international cooperation, and what I was wondering about this, how would you prevent this sort of race to the bottom unless we have cooperation? So for example, we have two nations where one is limiting the amount of space created and the other one is just doing whatever they were doing before. Then the non-compliant nation would come ahead. This business.
This is a very real risk, and what has worked in the past and led to the conclusion of international convention is mutual fear. I mean, the whole body of international space law was created in the Cold War, where each superpower was afraid that the other superpower will gain the space race, and now we have a new space race. So they actually wanted to limit the benefits that could derive therefrom, and therefore they concluded some international conventions to mitigate potential losses. This is not what you will hear. You will hear about nice humanistic motives. Yes, there were these things, but actually what played a crucial role was mutual fear. And perhaps mutual fear could help us in this instance too. Now, regarding the rest of things, we could try these behavioral insights and see if anything can work out. But you're right. We have a race to the bottom. There is great reluctance for regulation, especially in the United States, where strong lobbying from the space industry is also being exercised, and we have an entanglement of the space industry with the tech companies, especially SpaceX, and this complicates things. This is the usefulness of behavioral insights. We can try them and see what happens.
Thank you. Any other questions in the audience as of now? If not, I'll take a chance myself and ask a question. I'm afraid that history will have to repeat itself for us. We need for this kind of thing to be managed well. What would that kind of accident be that the nations have to get the legislation up to date afterwards?
Yeah, something really impressive that causes huge problems. Maybe that I don't know, one very bad scenario would be that the low Earth orbit is rendered to a significant extent or even completely unusable, because we had some instances where the amount of orbital debris was significantly increased, mainly when the Chinese destroyed a satellite of theirs in 2007, and increased the amount of space debris in low Earth orbit by 1/3. It created around, if I'm not mistaken, about 5,000 orbital debris, but I'm not sure about the number. But still, this created an outcry among space lawyers and among policymakers. Things, as usual, are quite complicated. To an extent, the Chinese did not want to do this. It appears that it was an initiative of the Chinese military without civilian approval, but it happened nevertheless. And still, we could achieve no binding rules despite this phenomenon. So it would have to be something really bad that creates a public outcry and will push for mandatory rules.
Thank you for the answer. Let's hear one more round of applause for Michael on this presentation. Thank you for presenting. Thank you. Next, coffee break before we head to the final track of the day. So we're going to come back here about 20 minutes. See you in 20 minutes. Couple of minutes and we will have the last track getting. Ei, no nyt kuuluu taas. Yeah, so everybody's there, still plenty of seats all around the hall. You can come even to the front row because I've heard there might be a musical number coming with these guys presenting. So when they start singing Vanha Holvikirkko, all the participate to that one. No pressure, guys. Yeah, but yeah, let's wait a couple of minutes so everybody has time to come in here. I wanted to everybody taking the coffee out there, when they hear I'm starting the session, then they start realize, oh shit, I need to be there, and then they start walking in here. So I'll try to get my voice heard so everybody actually. And why is this microphone not connecting from time to time? It's having some kisaväsymys, as we say in Finnish. 3 days we've been listening to lots of different kind of phone. There we go. Thank you. Even the microphone. Change the mic. Testi. No niin. Okay, this should be better, hopefully. Knocking on the wood here. But yeah, let's start the final stretch of the event. For most of the attendees, obviously there's going to be some additional program after this, so please enjoy that as well. But I was gonna say, welcome to the stage, Mikko and Jaakko, but they're already there, a little bit eager to present, but let's give them a huge round of applause before they start presenting. The stage is yours, boys. Let's get the show on the road.
Yes, hello. So today we will be presenting about NaviSP deployable satellite navigation antenna, not a musical performance, I'm sorry. But yeah, let's go. So my name is Jaakko Kaartinen. I'm a senior mechanical engineer and I work in Hult, part of Go4.
And I'm Mikko Kärnleino, antenna engineer in Radiantum, and talking mostly of the antenna here.
Yes. So a short introduction to our project. So this is part of NaviSP program, so funded by ESA. So shortly about the project motivation, the usage of Ka band antennas are quite limited. So there is a need to deploy our Ka band antennas. So so with the increasing number of satellites in low Earth orbit, there's a need for precise navigation. So that is the project motivation. Shortly about the consortium. So as Holt, we worked as Prime, and Radiantum, RF engineered, basically, or antenna designed, and FMI, Ilmatieteen-laitos, space expert in this area. So shortly about the main requirements. Mechanically, of course, it's deployable. Also small enough to fit in a CubeSat. So it was required to be n times 20 centimeters, but it's a bit smaller. So so the mass should be also minimized for the CubeSat standard. And then the temperature range it's quite high, I guess, for the operational of the antenna performance. And you can.
And from the electrical requirements, the antenna for navigational purposes, it needs to be dual circularly polarized. It needs to have operation in Ka band, so in millimeter wave frequencies, and the 3 dB beam width should be plus minus 30 degrees.
So shortly about the project results and achievements. In work package 1, mainly in FMI's expertise area, so we identified missions for this kind of Ka band utilization. So in-orbit servicing, refueling operations, hardware upgrades, debris removal, and stuff like that. And also low lunar orbit navigation purposes. So then we jump into the work package 2. We did a lot of mechanical concepts and designs, mainly as a trade-off study for the antenna deployment mechanisms. So there's a bunch of 3D prints that I made, and also CAD analysis and motion analysis.
And we had like several different antenna concepts, which we then compared and which then Jaakko made, and we had then quite extensive electrical and mechanical trade-off analysis of those. I think in the next slide. Yeah, so we compared all the different concepts quite extensively, and then in the end chose the design you are seeing here, so this stack patch solution.
So yeah, a bit more for the mechanical design point of view, and then the basically results from the stacked patch antenna performance and mechanical side of things. Some numbers about the model analysis. This hasn't been done vibration tested, but some analysis has been done. There are some results from the thermal simulations. The thermal deviation or deformations were quite low, which was required for the stacked patch antenna design, which is part of the 120 plus minus temperature range. Yeah. Mechanical testing was also made. Basically, two requirements required: physical testing, deployment, of course, because it's deployable, and then mass was well measured, which was quite easy enough and matched with the CAD files as well. And yeah, compliance pretty much easy when the temperature deformations were done, so and analysis were done. No issues with the deployment systems. It's quite robust and simple anyway. So the deployment isn't that long, but it was required by ESA, and it's 1.2 millimeters. But there's a benefit, of course, with the floating design with the stacked patches, because it's thermally quite stable. So the deformations stay in. It was 5 microns theoretically, or yeah. So that's one benefit for the floating design and deployable design.
Yeah, and from the electromagnetic design point of view, well, you can here then see maybe a bit properly or better what is the actual structure of the antenna. So on the bottom side, there are 2 connector points that are used to feed the different circular polarizations. The antenna has 90-degree hybrids made with microstrip realizations to, well, essentially make the polarization. And there are three patches on top of each other that make the radiation pattern as it should be. So on the bottommost is the one where we have the hybrid, and then the two patches or parasitic PCBs on top then guide the radiation. And we did also quite extensive electrical testing of the prototypes. First, we contacted our friends here in Aalto University and measured the antenna and verified its operation here. And then we went to ESA premises in Estek to finally verify that all the requirements, electrical requirements, are truly met. And you can see here on the bottom left the S11 and actually the S parameter results, and we have good radiation there or resonances, and then there are also the two radiation pattern results showing the wanted radiation from the antenna. And we were able to feel the electrical compliancy. We have good radiation in both left hand and right hand circular polarizations. The minimum beam width across the whole 3D space is slightly less than targeted in the LHCP polarization, but like the average is well within line of the requirements, and also the actual ratio of the antenna is quite well. And we were also able to verify that for these navigational purposes where like very accurate phase performance and very low group delay variation is required, the antenna works very well. Although we also found out that these very accurate group delay measurements, they are very challenging at these millimeter wave frequencies.
So yeah, a bit about the next steps of this project. Well, during work package 5, there was required to make a path forward. So we recognized 3 scenarios for development of this current antenna. Well, the scenario 1 is the preparation of the current design. There's of course optimization to be done as an engineer, so some optimization of the deployment mechanism, for example, from mechanical side would be crucial. Well, could work like this maybe, but not optimal, of course. In scenario 2, this could also be fixed version, so deployment is of course always a risk. So making a fixed antenna version could be more robust and a safer version, but of course then it probably wouldn't be as thermally stable. But yeah, and scenario 3, the same kind of deployment mechanisms could be applied for different frequencies as well. So maybe we could benefit a bit more from the deployment itself and make it more compact or deployment efficient, so we get a further or bigger deployment, of course, and we can stow it to a smaller size, basically. And yep, here are some contact details from my side. Juho Veteläinen was the project manager for this program, and mechanical engineer Mikko and Riku was RF designer, and Harri Haukka from FMI, and Antti Kestelä. Harri Haukka was the project manager for this from FMI side. Yeah. I guess that's all. Yeah. Thank you.
Thank you for presenting. You're not off the stage yet, because I'm going to give this crowd a chance for questions regarding this topic. Any questions as of now to these fine fellows? If not, okay, we'll get one question from there. Excellent. Even better.
Gain of the
Yeah, the gain of the antenna is around 9 dBi. So, yeah.
Not too bad.
Yeah, not too bad, but of course, not maybe that directly as well as like let's say your very high gain millimeter wave antennas, but of course then that's limited by the wide requirement for the quite wide beam width, plus minus 30 degrees.
Exactly, yes. And I would like to repeat the same question as the technical officer presented the final presentation. Picture of deployment before and after that would be beneficial to realize how we protect the process. Sorry? Deployment. So how does it look before deployment and after? So you still don't have that picture.
Yeah, that's actually very good. Well, I think we might. I think you have video maybe of that.
You mean before performance before and after deployment?
Yes, so that we can see what is actually deployed when you deploy it.
Yeah, so I can show you up closer, but the main top plate is deployed, and then but we didn't do any performance testing of the RF side of things before and after, before deployment.
Okay, that was all from my side. Thank you.
Thank you. Any other questions as of now? If not, then I'll let you off the stage with a huge round of applause. Thank you both for presenting. Yesterday, at least in the defense track in Lumituli, we were discussing quite a bit about the GNS interference, and we're going to have Matias Mikkonen discuss this topic a little bit more next. He has done experimental analysis on it. So let's get Matias to the stage with a huge round of applause. Welcome to present. And this mic is active for you.
Yes, thank you very much for the introduction. Indeed, my name is Matias, and I'm an assistant research scientist at the Finnish Geospatial Research Institute here in Otaniemi. And the work I'm presenting today is an experimental analysis of GNSS interference mitigation with a small antenna array. As some of you may well know, array signal processing or array antennas are not a new invention in any way, but with the rising number of GNSS interference events and the increasingly stringent requirements for GNSS-based location and navigation availability and accuracy posed by, for example, applications such as autonomous navigation and so on, we feel the topic is perhaps even more relevant than ever before today. And as such, the intention of this presentation is to send the message that we recognize the potential and there is work being done in this direction at FGI. This brings me to the outline of my presentation today. I will first introduce you to the experimental dataset, after which I will dive a little bit deeper into the actual jamming signal considered in this work and some of the techniques that we implemented in order to detect the jamming signal. Then we'll move on to something a little bit more array processing specific, so we will discuss direction finding techniques and some relevant methods. And finally, introduce some results on jamming mitigation so that we can actually maintain positioning performance under heavy levels of interference. So firstly, the dataset was captured by the European Space Agency at GEMER-Test 2024 using a coherently sampled 4-channel SDR to sample the elements of a uniform rectangular array antenna. And FGI obtained this dataset actually through participation in the EUSIPCO, or European Signal Processing Conference 2025 Phased Array Signal Processing Student Challenge, for which our team was actually awarded second place. The specific scenario considered in this dataset is a ramp jamming scenario, so the jamming power increases in power over time. So the jamming power is initially very low, but in the background, a jamming signal increases. And the objectives of this activity were then to detect the accurate start time of the jamming event, estimate the direction of arrival of the jamming signal, and mitigate the effects of the jamming. And as promised, here is a description on the specific jamming signal. So first of all, autocorrelation analysis revealed that the jamming signal is a pseudo-random noise, or PRN, sequence repeating with a period of 1/3 milliseconds. And a simple PSD analysis also indicates a one-sided bandwidth of approximately 3 MHz, centered at 1575.42 MHz. So the conclusion is that this jammer completely covers the L1 GNSS navigation band. And the jamming power is quite strong, indeed approximately 35 dB above the noise floor at the end of the scenario. Our first objective was to detect the start time of the jamming action, and for this we implemented 2 discrete techniques. The first one being a statistical test, a chi-square test developed here at FGI that compares the empirical sample amplitude distribution to the expected distribution of thermal noise. And as we can see in the figure on the right, the CST reveals the presence of the jamming signal quite accurately as soon as the signal is above the noise floor in power. And since now we are operating with an array receiver, we were able to generalize the CST quite simply by taking the median of the metrics from each of the 4 antennas. And we found that this allowed us to lower the detection threshold without increasing the probability of false alarm. And just out of curiosity, we also implemented a post-processing approach that leverages the characterization that I presented here before to actually reveal the presence of the jamming signal throughout the entire dataset, although it's not detectable by the receiver before it's above the noise floor in power. Our next objective was direction finding of the jamming source. For this, we considered 3 distinct techniques. The conventional beamformer and music algorithm-based estimates converge on the same value very near at the same time as the CST detects the jamming power above the noise floor. And similarly to detection, post-correlation analysis confirms the direction of arrival throughout the dataset. And here on the right-hand side, you can see the reference frame in which the direction of arrival was computed. And we were also able to obtain an estimate of the attitude of our reference frame in a global reference frame. This was done by performing direction of arrival analysis on the actual satellite signals. And this is possible because the satellite positions are, of course, known to the receiver. Here, what we have done is aligned the north estimate of our local reference frame with the north in a global reference frame, in this case just on a simple map. And then what we have done is kept the jammer direction of arrival with respect to the north estimate in the local reference frame fixed with north on the map, and there you can see that we obtained a relatively accurate direction of arrival of the jamming signal on a physical reference frame without knowing the attitude of the receiver beforehand from any external data. And our third objective was indeed jamming mitigation. There are several discrete power minimization-based techniques to mitigate jamming via phased array signal processing. Our first one, or our first approach, was to find the optimal steering angle for the conventional beamformer. So if you're familiar with the field, this basically means that we restrict ourselves to choosing only a phase shift for each of the channels before we sum them together. And in this case, a single interference source is very likely to fall into a null region for some steering angle, and since the main beam of the very small array is quite broad, it will still facilitate reception of the GNSS signals from throughout the sky. And we named this very simple technique blind steering. And although it's far from optimal, it's very easy to implement and also easy to implement on very cheap analog electronics. And there's also some research done in this direction together with Aalto University. We also implemented a somewhat more advanced technique that leverages the second-order statistics of the jamming signal. So if anyone is familiar with a quite famous MVDR beamformer, the power inversion beamformer is quite similar, except that instead of enforcing a directional gain constraint, we only enforce a magnitude constraint on the array steering vector. And on the right-hand side here, you can see the array response pattern of the power inversion beamformer under jamming. And it's quite evident that there is a single sharp null in the direction of the jammer, while the rest of the sky is quite unaffected. Of course, the array reception pattern doesn't tell you anything about positioning performance under jamming or reception of the satellite signals, and for this we are presenting concrete location-based estimates. Some key notes about the PVT error statistics during the scenario. Availability of the PNT solution with both of the phased array signal processing techniques is 100%. PNT processing was performed using FGI GSRX, which is an open source software-defined receiver developed at FGI. It's open to anyone on GitHub in case you're interested in experimenting with similar datasets. Here we are presenting the position errors over time in the images on the right. So indeed we considered both Galileo and GPS constellations separately. And in the figures on the right, we have indicated the timestamps at which the single antenna reference that we also computed loses track of the satellite signals. And it's quite evident that it's far before the end of the dataset, while both of the array processing techniques can maintain similar performance to the nominal section throughout the dataset. For some project conclusions and views on future work, indeed it's been clear for quite some time that phased array signal processing has significant potential for resilient PNT. Resilient PNT CRPAs, or controlled radiation pattern antennas as they're called in the field, are becoming increasingly available in also civilian applications, having been removed from the United States munitions list, for example, last September. And the intention of this change is to ease the use of this technology in developing safety-critical civilian applications. One interesting thing to note as well is that future GNSS constellations are expected to transmit at higher carrier frequencies, which will enable more compact-sized array antenna systems on the ground as well. And future work considered at the FGI, we are particularly interested in developing adaptive dual polarized array antennas to mitigate multipath propagation signals, for example. That's it from my side. I'm open to any questions.
Thank you for presenting, and thank you for being so open to questions. So, do we have any questions in the crowd on this topic? Let's get the mic over there.
Hi, and thanks for the presentation. Just one question. Did you use any antenna phase and gain calibration, or is it just assuming the idea?
Yeah, very good question. Thank you. Indeed, we are operating with a very idealized model, since with this dataset we did not obtain any calibration information. One thing to note is that the situation is quite static. So for that reason, the phase center variance resulting from array signal processing itself is very minimal, or at least quite constant.
Thank you. Any other questions? Yeah? No hands raising at the moment. So thank you for presenting once again, and obviously further questions can be maybe sent via email later on. Thanks. Next on, we have the second final presenter of the day. We had Magnhild Egg presenting about antenna array prototypes. Do we have her here somewhere? We do indeed. Excellent. Do we have her presentation there as well? Nice. We even have your presentation here. So welcome to the stage. Thank you. With a huge round of applause while at it. There's the remote, and you can use this mic.
Yes. Hello. Hello. Is this okay?
Yep.
Yes, my name is Magnhild Egg. I'm a PhD student at the Norwegian University of Science and Technology. I work at the NTNU Small Satellite Lab, and I'm here to present antenna array prototypes that we have made for our new satellite with a GNSS receiver. So The NTNU Small Satellite Lab is a research team consisting of bachelor students, master students, PhDs, postdocs, and other researchers. We make small satellites for research missions. We're making our third satellite now with a type of technology we haven't had that much experience with, which is GNSS receivers. We want to make a satellite with two missions. The first mission is GNSS reflectometry, GNSSR, for ship detection and maritime surveillance. The second mission is GNSS interference detection and localization, which means we want to locate jammers and spoofers. So at this stage, we're still in the early development phase. So this is just a simple sketch of the mission concepts. On the left, we have the GNSS-R mission. We take advantage of the fact that the GNSS satellites are constantly broadcasting signals across the planet, and then our receiver is supposed to pick up the reflected signal being bounced off back from the Earth, and then you compare the reflected signal with the direct signal, and then you can try to detect some anomalies of the area you're observing. So for this mission, we know what we want to do, and we need the receiver to do the thing very well. It needs to be a quite specialized receiver. It has to be very sensitive. It has to be able to detect signals so for lower than minus 60 dBm. And to compare this with the interference mission on the right, here we want to basically do spectrum monitoring and use different algorithms and methods to just try to detect different types of jamming and spoofing. If you look at the picture here, it's very focused on the polarization of the signal. We want to look at that, but we also want to use different methods to try to locate the jammer. So in this case, it's a bit challenging because we won't necessarily know what we are looking for. So this mission would require a more flexible receiver. And it's also important that it can withstand some sort of like maximum, like worst case scenario for very high power transmitted from a jammer. So in this case, we've set a limit at 70 dBm. So we want to try to combine these two missions to fit into one hardware receiver. So we want to make a customized antenna and a customized RF front end. We want to build it using commercial off-the-shelf products and open designs in the scientific literature. So we think we're probably using a 6U CubeSat with deployable side panels. It will probably be then 30 by 40 centimeters. So this is just an example image from Nano Avionics showing something like that. So at this point, we're trying to just figure out how to make the right thing, not necessarily how to make the thing right. So our requirements we've set is that we want to look at the GPS L1 band and L5 band. We want a gain of at least 15 dBi. We want to be able to receive both right-hand and left-hand polarizations. And we want to do phase steering. So based on that, the design concept is that we're going to have a 3x4 planar array with patch antennas. And to simplify the wiring and to try to limit the number of ports that's required for the digital part of the receiver, we decided to combine 3 elements at a time into a linear sort of cluster. And then these 3 elements are hardwired together. And then we sort of just copy-paste that design 4 times. This way we get phase steering across the 4 clusters, which will be then the across-track axis. We will not then have phase steering in the other direction, so to try to get a long track pointing, we will just have to point the satellite. We also are going for linear dual polarization to synthesize both the right-hand and left-hand circular polarization. So this is a bit more detailed for each of the 3 element clusters. We are using the patch element based on the specifications from the MIR instrument developed by the University of Catalonia. It's basically most of those specs with a few tweaks. There's also the dual home filter for the L1 and L5 frequencies, and a microstrip power combiner, and then LNA. So this is, we decided to split the RF front end and the sort of antenna part to make it a bit quicker to prototype. With the antenna testing also, we decided to 3D print these frames, making it easier and quicker to adjust the sizing and spacing between the elements. Yeah, it's we had to produce everything externally. I have the components assembled and everything externally, so it's taken a bit of time. This is only the second iteration we've had time to make. But based on these components, we can try to do some calculations on the link budget and tolerances. So in a scenario with the GNSS-R, we can make some assumptions with the GNSS satellite and our CubeSat with their altitude, and then we can calculate the SNR at the receiver, at the output of the RF front end. That's about minus 140 dB. So this is just a pure signal strength and not taking into account any like coding gain or anything. And then if we compare that to a scenario where we have the same hardware and altitude, and then we have a jammer at the Earth's surface, the jammer would then have to transmit at 140 dBm in order to damage the equipment. So this means that at this moment, the sign here has the potential to we can increase the sensitivity for the receiver. We can give it more gain and try to push the sensitivity further without risking that the sensitivity makes the same hardware vulnerable to get fried, basically, by the jammer. So that's good. We also did some radiation pattern testing. At the moment, the electromagnetic characteristics seem quite okay, with a gain, with an array factor gain of, yeah, at the most 16.5 dBi, which is good. But then the RF front end, the electronics, have very high loss, at least 8 dB and up loss, and this is very high. This can be attributed to the fact that many of the off-the-shelf components that we have used during development and testing have not had available simulation models, and the manufacturers haven't answered our request. So this makes it a bit difficult to make good matching networks and simulate and everything before we produce and test it. So the main conclusions at this point is that hardware design has capacity to being improved further without the two missions. The way we have defined them so far are mutually exclusive, and further it shows that using these proprietary components sometimes make the design process go a bit slower. And also that making these kinds of designs when you can't produce the prototypes in-house is a bit slower than you might expect. So, thank you.
Thank you for presenting. And once again, to the crowd, do we have any questions on this topic as of now? Most likely, questions can be sent via email later on. But for now, thank you for presenting. Last but not least, I'm now stretching for the final home run, I would say at this point. We're going to have somebody, one of the guys who has actually helped organize the event, Ville Lundén, coming up with the final presentation of the day and then external activities later on. But let's get Ville, the final presentation of the day, to the stage with actually a big round of applause. Please, welcome to the stage, Ville.
Thank you for the really kind introduction. So yes, my name is Ville Lundén and I'm here from Aalto University, and I will be presenting to you our flexible high-performance metasurface antenna solution that we have been developing for both terrestrial and aerospace applications under the Diamond project funded by the Business Finland. It's a research-to-business type of project. And the motivation behind our work is that different platforms are nowadays becoming increasingly small in size, whether it's satellites, unmanned aerial or ground vehicles, surface vessels or something similar, but their performance requirements are not decreasing, actually quite the opposite. The same applies also then for the antennas on board these platforms. And well, there is a challenge because typically high-performance antennas, especially if you require high gain or some very specific beam patterns, require large antennas. How do you fit these on the small and lightweight platforms? We have been looking at this problem. A solution that we are proposing are these holographic metasurface antennas. This is a technology that can provide many of the benefits that we are looking for, and these have been shown by many research before to be able to provide features such as excellent radiation pattern control, very simple feeding mechanisms. Just a single monopole feed can be sufficient. This is a great advantage compared to, for example, phased array antennas where complex feeding networks can be a challenge. And the planarity and low profile of these HMAs is a benefit compared to many reflector type antennas that require deployables out of the antenna plane. There are some drawbacks, however. These metasurface antennas are relatively large in area. Of course, it depends on the wavelength and what high-gain antennas aren't large, but they are also implemented on rigid panels due to challenging material limitations, to which I will come in a moment. And now, how do you put a large continuous panel on a small satellite and launch that into space? This restricts the applicability of these antennas on the compact platforms. Now we ask the question, could we make these flexible so that we can stow them and deploy them on these platforms later on? Well, now you could think that maybe just divide the antenna into rigid antenna panel into sub-panels and deploy them with hinges. But this is not really possible due to the way these HMAs work. So what the HMA is a continuous surface or antenna surface that has a continuous impedance modulation if you have some kind of sub-panel deployment, you introduce discontinuities into this panel, and this will destroy your radiation pattern performance. So this impedance modulation, with it we can control how the wave propagates on the surface, and this in turn determines what is the final far-field radiation pattern that we want to achieve. In practice, this is achieved by dividing this aperture into a grid of small sub-wavelength unit cells, where each unit cell has a little patch element, metallic patch with geometry that we vary, and through this we can vary the surface impedance and then control the wave propagation and far-field pattern. But now back to the flexibility challenge. You might ask why there aren't any flexible HMAs if these are so beneficial. This boils down to a challenge with the trade-offs. So, of course, if you want to have some highly flexible substrate, you need to look at very thin structures. But kind of practically available materials have typically low permittivity. But then from the RF performance side and from the mechanical, RF performance side, a higher thickness and higher permittivity would be beneficial. So we need to address this trade-off, and identifying the most suitable substrate is the critical step here to make it happen. We need to consider the flexibility, thickness, permittivity, also high frequency characteristics. We don't want the substrate to be too lossy. And then, of course, manufacturability and cost considerations are something to think about. After careful search and investigation, we realized that the best alternatives still have quite low permittivity, around 3. And this means that we just need to compensate somewhat with a bit higher thickness and increased unit cell size. So the discretization of the aperture is not as accurate. So there is some trade-off with the flexibility and the RF performance. But once we have selected the substrate, what we do in practice is that we select the unit cell geometry, we design it and we simulate how changing the geometrical parameters affect the impedance of the unit cell. After this, we can extract that as a function of the geometrical parameters. And in the third step, we actually calculate what would be the ideal impedance distribution on this surface. Then on the fourth step, we take these unit cells that we have designed and populate our aperture with the best possible set of unit cells to produce the desired radiation pattern. And then in the fifth step, it's time for verification through full wave simulations and manufacturing and testing. All right, so our first prototype shows very promising results. We have an antenna with a gain over 20 dBi and great cross-polarization levels. Side lobe levels are also very low, and the bending radius is less than 1 centimeter. So this is definitely something that you could, for example, roll for low volume stowage in your applications. This is a 20 gigahertz antenna, and the size of it is about 222 millimeters. It's a square with this side length. Well, in the next steps, we aim to improve the flexibility further, and this is going to be achieved with a slightly different kind of approach and improved approach in the unit cell design. And we are also currently looking into optically transparent solutions, which would further widen the area or applicability of these antennas, for instance, on solar panel arrays, on spacecraft or other autonomous platforms. We also aim to demonstrate more operating frequencies, so we can cover a much wider range of frequencies than just 20 gigahertz of the first prototype. And we also plan to design antennas to operate in the curved configurations, because this allows us to integrate this, for instance, directly onto the fuselage of some aerial platform. Then active beam steering is also something that we aim for in the future. Whilst conclusions, satellites and small terrestrial platforms still need large and lightweight high-performance antennas, and these flexible holographic metasurface antennas are a promising approach to solve this problem, because they can provide high-gain, multi-beam, multi-frequency, and other advanced capabilities. And this flex PCB type of implementation also enables very scalable, low-cost manufacturing. And well, the prototype performance, it is very promising, and new features are currently under active development. And there is also a technology commercialization planned for this now in beginning of this year. Thank you. Happy to answer any questions.
Thanks for the show, and as per said, open for questions. So the stage is now yours, dear audience. Do we have any questions right now? Everybody's about this eager to go for lunch and everything. There's one question at the back. Can we get the microphone over there? Please keep your hand raised up. Over there.
First of all, thank you for the presentation. For regular isostrip patch antennas, you have the radiating element and the substrate, and then on the other side a ground plane. And the distance between the ground plane and the radiating element is much bigger than for flex PCBs. Does that affect the antenna in any way, or the manufacturability?
Thank you for the question. It does not really affect the manufacturability. So, of course, at low, well, for a patch antenna, a low substrate thickness will limit your bandwidth, but this is not directly the case with this antenna. So it's a slightly different, or a different kind of operating principle. So I would say it's more related to the operating frequency. So the lower thickness limits how far we can go down in frequency.
Okay, thanks.
Any other questions as of now? If not, thank you, Ville, once again for presenting. Thank you. You're off the hook for now. I would say that's it. That's it for now. We have had 3 long days of presentations, and finally we're getting the magician behind the curtain coming up to the stage as well. Let's welcome Jan Brax for one last time to the stage. He has to say a couple of words regarding the 3 last days we have had here today. Jan, how are you doing, man?
Doing fine, and I would actually like to ask the organizing team we have very tight schedule, because the next happening is starting already 5:30, and that's why we are squeezing everything now here. But behind this happening is a huge amount of work with a lot of people. And I was hoping to get to this floor here. First, my research group with a lot of volunteers. And then we have another big part of people who are streaming the whole event and doing all the digital background work, what has been done. This is a very small fraction now here. The digital streaming of the whole event has been made by Polygame. And can we get Polygame also to the floor here? And I'm sorry, it's a bit of unofficial because some of the other sessions are still working. We would like to just take the photo with organizers, but I'm trying to get also, we have almost like 40 people in the program committee, and there is like 100 people here everywhere, but we just are, everybody are so busy. Some of them are already presenting our stuff in Marcio. Some people need to do like other things. So, yes. Daniela, you are part of the team. You are our social media ambassador. Lucas, you are our conferencier. Let's start. Yeah, that's true. Let's wait a bit. We will take first picture and then we will ask everybody what is happening, because we have to take more pictures.
So let's wait 5 minutes in dead silence.
Yeah, let's wait 5 minutes in dead silence.
While we're waiting, I would still one more round of applause for Jan for making this all happen at this point.
Yes, and I hope we can make it happen next year again with your kind help, and everybody sending abstracts, and then we're going to get a huge program. But yeah, we probably need to wait 5 more minutes because you ended a little bit early.
So then you have 5 more minutes to give us a sneak peek of what's going to happen next year then.
What is going to happen next year is actually unknown at the moment. We are on the crossroad. We have negotiations with many players, and one of the options is go to Messukeskus. We have wonderful partner, Helsinki Messukeskus, who is making big fairs in a big fair center, but it has all the like lifts and trucks and facilities for storage and making really big exhibitions, and we could make the whole. So, Kaisa, Miika, come to the floor. People are coming. So there's just, don't hurry. We have a lot of more people to come, but we try to get the group picture soon. So that means that we still negotiating with many players. We have been growing. Heidi, you have to be on the picture. We are just collecting people to the picture. We have crossed 2,300 registration lines, so this is like quite crazy. We never have had so many registrations. Jari, you are part of the team. You are our press secretary. So a lot of side happenings have been happening. There was TV interviews, radio interviews. Yes, and we still have some minutes to wait. We don't know. We hope that somebody will take a picture.
There's at least one photographer over there with my tablet. So.
Yeah, Mikko Punnala is here. But I don't know. Maybe we have a nice round and tell what you did during this conference on the backstage or on the stage.
Well, I've been on the stage for the whole time, so everybody knows what I've been doing. I've been just like yappering here to entertain you, and hopefully I've done a good job. And maybe next year again. You never know. Thanks.
Yes. Right. Hello. I'm part of the Polygame stream team. So while Lucas here, make sure everyone has a good time on stage and in front of you guys here in the auditorium. We have been working to make sure that people who are participating online have as much as the same experience that we can. So we have some kings in the beginning, but I hope by today we have managed to iron it out, and everyone has having a great time. So if you'd like to add something.
Yes, so I was also making the stream view here, and then I also made a lot of technical stuff here, and then all-around man, plus then I also was yesterday here as a chair for the Kaleva, so it was very, very wide of a spectrum of jobs. So, but it was very fun. So next one.
Hi, Carl here. I've been part of the stream team, running the streams in the background, and doing miscellaneous other technology-related stuff.
Yes, I'm Karl Josep. I am here both with the stream team and also my wonderful colleagues at ASA. I've been building rocket launch controllers. I have been handling the streams, getting the links and everything, being some sort of a bit of a communication channel between our more Alta Satellites team and also Polygame. I have also been doing miscellaneous tech stuff here and there. And after this event, I will be cutting together a full video version. So you will have all the presentations. If you don't want to be on YouTube, then do send us a message. But we're planning to have most of the presentations cut and put on YouTube, so they can be enjoyed by people later on as well. Thank you.
And I'm Ville. I've been doing a bit of everything, a bit of everywhere where it has been needed. I've been driving the van, taking care of registrations, and also chairing some sessions, and I've been helping with the defense track as well.
Yes, I'm Marius. I have been organizing the expo this year. I have been at the registration. I have been searching screens 2 days long. Then we had enough screens, and then we had too many screens. And yeah, so yeah, that's how expo goes. It's always chaos, right?
Hi, I am Alexia, and I have been assisting with the registration desk and also been doing organizational things. So. Yeah, and I have also been participating in Shake Up Tech at Marcio, where we have been presenting our satellite setup to high school students that are willing to be part of the scientific community in the future.
Hi, I'm Topi. I have been handling name tags as a main priority here. Hope all of you found them easy enough.
Hey guys, I'm Augustinas. I'm from Alta Space Association, so also on behalf of all of us, we have been doing some side events, including some student panel discussions for students, CubeSat workshops, evening entertainments, and I've also been working with the setup and the application, so the Events Pro app.
Yeah, I'm Tuomas, and one thing to add to is what he mentioned, is that we'll be flying a rocket soon, and I'll be also organizing that, so join us at 17:30 at Otaranta to see those.
Hi, my name is Mayank, and I've been working with the setting of booth area, so setting up the booths in the expo area, and then helping with somewhere in the registration desk here and there.
Hi, I'm Walter Pitkänen. I've been helping also from the Aalto Space Association side with these previously mentioned stuff. So.
Hi, my name is Daniela, and I was trying to help with the communication strategy, so you might have seen us on newly Instagram, LinkedIn, and also we've introduced blogs, and with that being said, I would like to mention the colleagues that are not here and are part of the communication team and deserve a shout out, and that's Aziza Ibraheva and Daniel Guzman Mone, who really helped to make these beautiful visuals for the event, and we really work together really well, so we hope you enjoyed that. Thank you.
Hi, my name is Tuukka. I did a bit of this and a bit of that, but the main responsibility for me was the space and defense track. Thank you.
Hello, Kaisa Ahonen, Isabik, Finland. So we organized one session ourselves. I did a bit of talking here and there. I met lots of lovely people at our booth upstairs. So coming back next year, definitely.
Hi, I'm Mika, SFE Lab, mostly absent from our booth, but I also hosted a couple of sessions and gave a couple of speeches. and then attended a lot of other stuff, so and networked. So, and I was part of the program committee as well.
Hi everyone, I'm Francesca. I'm also from Alto Space Association. I was also helping a little bit with the side events, but primarily recruiting the lovely student volunteers. Over there we have some of them in the side. They had the pink tags, so thank you so much for volunteering. Yeah, and I hope you guys also enjoyed Windy Satellite Workshop.
Thank you. I'm Heidi. Thank you so much, everyone. I didn't do much. I was part of the program committee. I did some chairing, a presentation, but mostly I just enjoyed this extremely well organized, smooth conference. Thank you so much, everyone.
Hello, my name is Jari, and I have been mostly walking around and hanging around over here, but aside of that, I did some media relations and had a very nice chat with Markus Wandt over here yesterday.
Hello everyone, I'm Daniel. As you can see, I'm also from Alto Space Association. It was mentioned already what we did, so I kind of like filled in the gaps. So whenever we needed help with volunteers, I did that. Whenever we had to build screens, I did that. So wherever things were needed, I was trying to fill it there to keep everything smooth. And yeah, that's basically it.
Hello, I'm Anton, one of Jan's PhD students, and I was responsible for the presentation laptops and troubleshooting, running around the whole day. And yeah.
So. And finally, I'm Matti Mattus. I'm with the organizing committee, try to organize the remote session days, which were part of this program. And just as a small advertisement, it's an open society, so if you're interested, we can still get you in. Everybody is welcome to join and contribute to this community event.
So let's give a big hand to this crowd, which is only 1/3, maybe 1/4 of the crowd who was actually making this event and contributing in various ways. And we are basically no professionals in the conference organizing, but yes, this is what you can then ask from non-professional people who will be very good professionals in the future, at least on the student side. I'm probably already beyond hope in this one. All right, give a hand. All right, and now we will take one picture of everybody, and we try to...
Squeeze a little bit, and some of you guys can actually go to the stairs as well. That might be a little easier. And then we probably need to take another picture afterwards, because there is half of the people are still cheering and doing stuff there, like with the, but it's good to have something, and we try to get them to the web page afterwards, so there's something is for the history as well. Which one we're looking at? All of them.
Maybe we should also have one applause just for Jan, because he has been working on this the whole year. The whole year he has been sending invitations, programming the website. The whole event system, the back end was done by him. So one big applause for Jan. Yeah.
All right, and then we will meet next year.